Hello everyone, welcome back to General Chemistry. So the topic for today is mainly going to be periodic properties and trends, but we will also finally take a look at how to do Lewis symbols and Lewis structures. We will finally learn how to draw molecules and polyatomic ions. So yeah, let's get started. First, let's list off the periodic properties, or trends. So most textbooks will acknowledge 4 different periodic properties. I say there's 5, but then again, after a little mini rant you might hear from me later on in the video, maybe we'll go back to claiming 4, because one of the original 4 I don't think deserves to be considered a trend, but we'll get to that when we get to that. So the 4 official periodic properties are atomic radius or atomic size. It doesn't matter which term you use, because the greater the size of an atom, if you think of atoms as being spheres, the greater its radius and vice versa. So you'll hear people calling it atomic radius or atomic size, same thing. Number 2 is ionic size. How the size of an ion compares to the neutral atom that ion is based on. Number 3 is ionization energy. And number 4 is electron affinity. And this is the one that I don't really consider to be a true periodic trend. But again, you'll hear that rant from me when we get to it. Electron affinity. In its place, I would consider this unofficial 5th periodic property the electronegativity trend. I would consider this to be a more legitimate trend than electron affinity, but I'm sure people will disagree with me, and that's fine. But I'll try to make my case when I get to it. So let's go through these one by one. First off, we have atomic size or atomic radius. So let me bring up the following visual that helps illustrate what we mean when we refer to atomic radius or size. So in that figure you see a bunch of atoms, or a bunch of molecules actually, where 2 atoms of the same kind are bonded to each other. And what chemists like to do is they like to take half of the distance between the nuclei of 2 atoms of the same type, and they consider that the radius. Now you can probably tell just looking at the picture that that's not quite the same thing as the radius, but it's proportional to the radius, so close enough. But yeah, that's what we mean when we're referring to atomic radius. So it's not the literal radius, but it's approximately the radius. It's half the bond length between 2 atoms of the same kind. Anyway, let me switch over to this other picture where we get to finally see the trend. I don't know why I added the word finally there. It's not like you had to wait too long. But yeah, so looking at that picture, basically it's the periodic table again, but this time it shows you the relative sizes of the atoms. So first thing I want to call to your attention is that first column, hydrogen, then below it is lithium, then sodium, potassium, rubidium, cesium, francium. You notice the further you go down a column, the bigger the sizes get. Another thing you might notice is that the sizes get bigger as you move from right to left. So let's take the second row, for example. We've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. It's a little bit harder to see, and you might want to pause the video and maybe squint a little to see it. But yeah, the atoms get bigger as you go to the left, or in other words, smaller as you go to the right. If you compare Maybe don't compare two atoms that are right next to each other, but maybe atoms that are two spaces apart, it might be easier to see. If I compare boron and nitrogen, I can clearly see that nitrogen is smaller than boron. If I compare oxygen to carbon, I can barely see it, but oxygen's definitely smaller than carbon, and so on and so forth. So let's go ahead and try to explain these trends. What's going on? Well, the increase in size as you go down a column, some people probably already know what's going on with that. Let's take a look at hydrogen. So hydrogen, 1 proton in the nucleus, usually no neutrons. And then you've got just 1 electron orbiting around it. We're using the planetary Bohr/Rutherford model here. But yeah, so that's hydrogen. Let's compare that with lithium. And I think I'm going to need more space for this one. So lithium has 3 protons in its nucleus, and I think 4 neutrons is the typical lithium atom. Some isotopes might have more or less, but I don't have those memorized. But yeah, lithium has 3 electrons, so the first 2 can occupy the first shell, and the third electron needs to occupy a whole new shell. Ah, now we see the reason for it. And I guess I should have written lithium somewhere else. Let's write it over there. Okay, so the third electron has to be in a whole new shell because the first shell is already full. If you write the electron configurations for hydrogen and lithium, you can clearly see that. For hydrogen, it's just 1s1. For lithium, it's 1s2. You don't have a 1p or a 1d or a 1f, so the next electron has to go in shell number 2 in the s orbital, in the s subshell of shell number 2. And yeah, there you go. So the whole reason that lithium is significantly bigger than hydrogen is because it needs to open up a whole new shell for its third electron to occupy, since there's no more room inside the first shell. And of course, you can use the same reasoning to explain why sodium is bigger than lithium. Its first shell and second shell would be full, and then sodium would need to open up a third shell to add its 11th electron. Sodium would have a configuration of 1s2, 2s2, 2p6, so that's 2 and 2 and 6 is 10. The 11th electron would have to be in the 3s subshell, so 3s1. So there you go, you've opened up the third level in sodium, so sodium would have a much bigger radius than lithium. And yeah, so basically you could say radius depends on the distance between the nucleus and the farthest out electron. Wherever your most distant electron is from the nucleus, that determines where your atom ends. If you think of the atom as beginning at the nucleus, it ends at wherever its outermost electrons are, where its valence electrons are. I hope you remember that term from last time because it's going to come up quite a bit in this video and maybe the next one. Okay, so that's atomic size. That's basically all there is to explain in terms of the trend for a column. What about for a row? Why is it that the atoms tend to shrink as you go further to the right in a given row? Let's draw a couple of different atoms in, let's do the second row of the periodic table. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. I don't think I'm going to draw all of them, but I'll draw a couple of them, maybe 4. Okay, so let's do Let's do lithium. I'm not gonna draw all of the individual protons. I'm just gonna put one big positive to represent the whole nucleus. And yeah, so you've got your first orbit, you've got your second orbit, or first shell and second shell if you'd like to use the terminology that we established last time. Okay, there's lithium. Next we've got beryllium. Let's see. I'm probably not going to draw these to scale, am I? Okay, that needs to be a little bit smaller. Okay, hopefully that looks convincing enough. So that's beryllium. Next up we would have boron. So boron. Oh, wait a minute, I forgot to circle this. Okay. Next up we've got boron. 2 electrons in the first shell, 3 electrons in the second shell. Let's see if I can draw it small enough. Okay, there's boron. And next up is carbon. So carbon, positive nucleus, and then 2 electrons in the first shell, and 4 electrons in the second shell. Let's see if I can draw that small enough. Okay, that looks good. So yeah, I think you can tell that they're getting smaller as you go to the right. If it's not that clear, then sorry for my bad drawing skills. But yeah, all of these have the same number of shells. All of these use up to 2 shells to hold all of their electrons. So what's different about them if they have the same number of shells? Well, what's different about them is how many protons they have. Lithium has 3 protons. Beryllium has 4. What was this one? Boron has 5. Carbon has 6. So even though they all use 2 shells, carbon is the one that has the most protons pulling on that outermost shell. They all have the second shell being their outermost shell, but only carbon has 6 protons pulling that outermost shell inwards. Boron has 5 protons pulling inward, beryllium has 4, and lithium only has 3 protons pulling in the outermost shell. And by pulling in the shell, we really mean pulling in the electron in that shell, or the electrons in that shell in the case of these guys. But yeah, that explains why atoms get smaller as you go to the right, because as you go to the right, the atomic number, the number of protons, increases while the number of shells used to hold the electrons stays the same. That's really all there is to it. More protons pulling inward, more, I guess, crunched up the molecule is, more condensed. But yeah, later on we'll talk, well, should we talk about it now? Or should we save it for later? Let me think here. Actually, let's talk about it now. Let's talk about shielding effects. Let's talk about shielding effects. Or perhaps you might want to add the word electron shielding effects. Okay, so there is something that we need to understand in order to justify a a bunch of exceptions to this pattern that we notice in the transition metals, and that's the idea of electron shielding effects. So if I look at the electrons in the outermost shell, in the valence shell of each of these atoms, then there is something important to take into consideration, which is the core electrons, the non-valence electrons. What effect do they have on the amount of pull that the nucleus actually has on these outermost electrons? Well, you could say that these electrons in the core electrons, they kind of protect the outer electrons in a way, partly, not entirely, but partly, from the effects of the charge of the nucleus. So you could say more core electrons leads to a reduction in the attraction felt by the valence electrons. If you knew your physics, I could explain this to you in terms of Gauss's law, but that's neither here nor there for this video. Let's see, reduction in the attraction felt by the valence electrons. This is what happens when I try to talk and write at the same time. And of course, even worse things can happen when I try to talk and write at the same time. But I digress. So yeah, the more core electrons you have, the less attraction that the valence electrons feel from the nucleus, in comparison to if you just had the same atom with the same valence electrons, but you just removed the core electrons. So if I had a lithium atom where I somehow surgically removed the two core electrons, if I had a lithium atom where I just got rid of the two core electrons, they were gone, and I just had the one electron in the second shell, like that, then I would expect it to be considerably smaller. I would expect it to be considerably smaller than the normal lithium atom, even if the remaining electron wasn't in the first shell, even if it was still in the second shell, because you don't have any electron shielding effects. So the way electron shielding works, think of it this way. The electrons on the inside partly repel the electrons on the outside. If you're sitting here in this second orbit, you're attracted inward by the nucleus, of course, but you're also repelled outward a bit by the electrons that are closer to the nucleus. So yeah, those repulsions overall subtract from the attraction. The attraction is still stronger, so overall you're still attracted, but yeah, there's a reduction in that attraction. You could say there's not a smaller nuclear charge, but it's kind of like you're experiencing a weaker nuclear charge. It's kind of like you're experiencing a weaker positive charge from the nucleus, and so we say there's a reduction in the effective nuclear charge. Not the actual nuclear charge, but the nuclear charge that you experience as a valence electron gets reduced, the effective nuclear charge. So in the case of this second shell lithium electron, over here, the effective nuclear charge is just the whole nuclear charge, is 3 protons worth of charge, while over here it's less than 3. Maybe it's 1, maybe it's 1.5, maybe it's 1.2. That's stuff that you can calculate and determine in the lab if you're curious, and if you have the right equipment. But the point is that this electron over here overall feels an attraction that's weaker than this one. It perceives this nucleus as having less charge than this one. But yeah, so that's effective nuclear charge. Sometimes it's represented with Z sub EFF. Z is the symbol that we often use for the atomic number, but it can also be used as a symbol to represent the nuclear charge. So ZF just stands for effective nuclear charge. Sometimes you'll hear people talk about another related concept, which is the concept of penetration. The concept of penetration, or electron penetration. Electron penetration, or is it orbital penetration? Well, I'll just say penetration in general, and then maybe I'll correct it in a pinned comment if I feel it's necessary. But yeah, the penetration effect. So what is penetration exactly? So when I first heard this from a student of mine a couple years ago, I thought it was just some weird attempt at rebranding the concept of effective nuclear charge to make it sound cooler. And, I tried looking around online and I didn't find many references to it, but after some serious and deep digging, I guess there is a distinction to be made between having a greater penetration versus a greater effective nuclear charge. Penetration isn't really about charge or the strength of the electrostatic force. It's more about the reason why electrons that are closer to their nucleus experience a greater charge. It's about distance from the nucleus. So we say that closer to the nucleus, if electrons are expected to be closer to the nucleus, then that means they have higher penetration. And yeah, I don't think penetration is the most appropriate word to describe this, but maybe their logic was that you can think of the electrons as, trying to get as close to the nucleus as possible, like penetrating it from the outside, and the electrons that manage to get closer have deeper penetration. I don't know what the reasoning behind the name is, but they call it penetration, which I think is not a very descriptive name, but it is what it is. So yeah, closer to the nucleus means greater penetration. So I would expect the 1s electrons to be closer than the 2s electrons. I would expect the electrons in the 1s subshell to have greater penetration than the electrons in the 2s subshell. And if you remember that n plus L rule from last time, basically the order from highest penetration to lowest penetration is the same order that you use for the Aufbau principle. So we would say that the 2p subshell would have less penetration than the 2s. The electrons in the 2s subshell actually can be closer to the nucleus than the electrons in the 2p subshell, even though they're both in the n equals 2 shell. But yeah, I don't think you need to worry about that too much, whether you're in high school or in college, but just mentioning it and covering it just in case, just to check it off the list. Anyway, that's atomic size. So Oh, no, we're not done with atomic size yet. Not quite yet. I still haven't finished talking about why we were discussing shielding effects to begin with. Let's take a look at the transition metals, and it might be hard to see with this chart, but let's pick out a couple of atoms in the fourth row of the periodic table. Specifically, I'm looking between columns 3 and 12, so from scandium to zinc. Let me see what I have. So it looks like, it looks like I see manganese appears to be smaller than iron. Mn appears to be smaller than Fe, which is not what you would expect. The trend is for the size to decrease as you go to the right. Let's see, what's another case like that? I believe it looks like copper is a little bit bigger than cobalt and nickel. So the point is, for these transition metals, for that first set of transition metals, you notice that the trend isn't really being followed as you go along a row. Sometimes it's decreasing as you go to the right, but sometimes it also increases as you go to the right. So what's going on there? Well, remember how the subshells of transition metals fill. Let's compare, for example, manganese and iron. So manganese is element number 25. It's got 25 electrons and 25 protons when it's in its neutral state, of course. And iron is element number 26. So 26 and 25. Let's take a look at their electron configurations. So manganese, of course, I'm just going to take a shortcut and write argon for both of them. Start with argon. And let's see, so that's going to be 4s2, 3d. Argon represents 18, plus 2 is 20. That leaves 5, so 4s2, 3d5. And then iron is going to be 4s2, 3d6. So if I were to draw models of both of these, if I were to draw manganese and iron, so let's take that to represent the nucleus of manganese. Let's see, so first shell is full, second shell is full, third shell not quite so full. And fourth shell will have 2 electrons in it. Okay, so there's manganese, and then I'll fill in the electrons later, of course. And then for iron, let's see, we've got first shell is full, second shell is full, third shell not quite so full, and fourth shell has 2 electrons in it. Okay, that's not exactly a perfect circle, but we'll go with it. And let me just highlight these in a different color so that we don't mistake them for orbits or shells. Yeah, let's do that so that we don't mistake them for shells. Okay, so first shell, 2 electrons. Same thing here. Second shell can hold 10 electrons, the 2s2 and the 2p6. Or no, not 10, 8. Okay, 2, 4, 6, 8. 2, 4, 6, 8. Third shell. So the third shell, first of all, the argon would represent 1s2, 2s2, 2p6, which we've covered so far, and 3s2 and 3p6. So that's another 8 electrons. So 2, 4, 6, 8. Those are the 3s2 and 3p6. Same thing for manganese. 2, 4, 6, 8. Okay, so that's 3s2 and 3p6 for both. Then we fill 4s2, so I'll do that. 2 electrons in the 4th shell. And then we've got, for manganese, 3d5. We add 5 electrons to the 3rd shell. So there's 2, 4, 5. And for iron, it's 4s2, 3d6. So we add 6 more electrons to the 3rd shell of iron. So that was 2, 4, and 6. Okay, so let me tally up my electrons here and make sure everything's accounted for. So 2, 4, 6, 8, 10, 12, 13, plus the 10 for the first 2 shells is 23, plus those 2 is 25. Okay, and here 2, 4, 6, 8, 10, 12, 14. That's 1 more than it was for manganese. So, okay, everything checks out. So, why is it that iron is not actually smaller than manganese in size, even though it's got more protons, even though it's got more charge pulling inward on the electrons? Because the electrons being pulled on are the 4s electrons. They're in the 4th shell, and even though iron has 1 more proton in its nucleus pulling on those 4s electrons, it also has 1 more core electron. It also has 1 more core electron than manganese does. So since you're adding electrons to the core as you go right through the transition metals, you're actually adding to the electron shielding effects. And sometimes you add just enough electron shielding that you more than make up for the addition of a new proton, and in those cases you'll actually see the size go up rather than down as you go right along the periodic table. So that's what's going on with the transition metals. Sometimes their sizes go up because as you add more protons and add more electrons, those electrons are being added to the core and adding to the shielding effects. If nothing else, for the most part, the sizes of the transition metals barely change at all as you go right to left. Sometimes you see increases, sometimes you see small decreases, and sometimes you don't see much change. But yeah, so there's the explanation for that. I think that takes care of everything for atomic size for real this time. I think I've said that 3 times in this video, and this is the 1 time that I actually meant it. Because that's what happens when you talk without thinking. Okay, but now that we know about atomic size, we can understand all the other periodic trends a little bit better on the basis of atomic size. And the first one that we want to go over after atomic size is, of course, ionic size. Ionic size. Ionic size. Okay, so for this, I don't think we're going to need to spend too much time on it, but let's take a look at the following visual. Let me turn that off and turn that on. Okay, so there they've shown you 2 different atoms and their normal monatomic ions. They've shown you the aluminum atom and its cation, the aluminum ion with a +3 charge, and they're also showing you sulfur, and below it they're showing you the sulfide ion, which is an anion. It's got a negative charge. So you notice that the aluminum ion is smaller than the aluminum atom, and that the sulfide ion is larger than the sulfur atom. Why? Let's first go over why cations are generally smaller than the atoms that they came from. Why are cations smaller? This is going to be really easy to explain. Let's say I'm looking at sodium. Suppose I'm looking at sodium. It's got electrons in 3 shells. First shell holds 2 electrons. Second shell holds 8. And then its 11th electron will have to occupy the 3rd shell. Okay, so that's the sodium atom. What about the sodium ion? How many electrons does the sodium ion have? The sodium ion is -1 electron, so it's got a total of 10 electrons. It has the same electron configuration as neon, incidentally. And that's going to matter in a bit. We're going to compare the sodium ion to the neon atom. But yeah, so here's your sodium ion. Let's see, and I guess I should draw that a little bit closer. Like so. And 2, 4, 6, 8. Okay. There's the sodium ion. Why is the sodium ion so much smaller than the sodium atom? Well, because you emptied out its outermost shell, so now its new outermost shell is a smaller shell. Since you don't have an electron in your 3rd shell anymore, you can still say that the 3rd shell is technically there, but if there are no electrons in it, then that just means that other atoms can get closer to the nucleus of the sodium ion. If there's no electron here repelling away the electrons on the outsides of other atoms that might be approaching, then those other atoms can get closer. So it doesn't matter if there's still a 3rd shell. If it's empty, it's as good as not being there. Okay, so yeah, sodium ion smaller than the sodium atom due to simply emptying out a shell. But it doesn't quite stop there. Let's compare the sodium ion to the neon atom. The neon atom also has 10 electrons. So neon atom also has 10 electrons. But you'll find if you experiment on it in the lab, or if you just look it up in a book, you'll find that the neon atom is actually bigger than the sodium ion. And can you think of a reason as to why? I think we've seen enough information where you could probably figure this out on your own if you pause the video, but I'm just going to go on ahead. So both the sodium ion and the neon atom have 10 electrons. In terms of electrons, they're equal. They're unequal in terms of protons. So the outermost electrons for neon and sodium are now, or sodium ion I should say, are both in the 2nd shell. The valence shell for both is the 2nd shell. You've got the same number of core electrons, so electron shielding effects are equal. but you have different numbers of protons. Neon has 10 protons, sodium has 11 protons. 11 protons pulling on your valence shell, on your second shell, will pull it in much more strongly than 10 protons pulling on that same second shell. Therefore, the sodium ion is not only smaller than the sodium atom, it's also smaller than other neutral atoms that have the same number of electrons, and I guess the only neutral atom with the same number of electrons would have to be neon. So I don't know why I used the plural there. But yeah, so the sodium ion and the neon atom are said to be isoelectronic. Isoelectronic. Isoelectronic means having the same number of electrons. Just like how we saw way back when isotopes were atoms with the same number of protons but different numbers of neutrons. Was there another iso term that we covered before? I don't remember, but way later, probably in the last video, we'll talk about isomers, which are molecules that have different structures but have the same molecular formulas. So whenever you see iso, basically that's Latin for same. Or maybe it's Latin for similar. I'm not quite sure. I don't know my Latin all too well, but whenever you see iso, think of something being the same. Whenever you see a word that starts with iso. Anyway, so these two species are isoelectronic, but they're not the only ones. You can actually come up with other, I guess they'd have to be ions that are also isoelectronic with the sodium ion and the neon atom. They'll form what's known as an isoelectronic series, and we will do an example of that. But first, let's go ahead and take a look at the case of anions. So we just explained why let me pull up the graphic again. We just explained why the aluminum ion is smaller than the aluminum atom. This would be true even if you don't strip away the whole shell, by the way. So if instead of removing 3 electrons from aluminum, you just removed 2, in which case you'd still have an electron occupying the third shell, even though it would be, 3 shells big, its third shell wouldn't be as big as it used to be before you removed the electrons, because now you've got more protons, or the same number of protons rather, versus less electrons that they have to pull in. So you will see a decrease in size even if you don't completely empty out the valence shell. Anyway, looking back to sulfur. So sulfur increases in size when you add electrons to it and becomes the sulfide ion. Why on earth does that happen? Well, think of people playing Ring Around the Rosie. That's the analogy that I like to use. If you have 4 people playing Ring Around the Rosie and then a 5th person wants to join, what happens? Well, the 4 people need to unlink their arms, they need to spread out a little bit more and make space for the 5th person to go in. Similar logic applies to sulfur and sulfide, but I'm going to use fluorine and fluoride instead so that I don't have to draw as many shells. Can I actually fit that on this page? Yeah, I'm going to try it. Let's wall this stuff off. Maybe if I shrink my scale a little bit, that'll help. But yeah, let's look at fluorine versus fluoride. I don't think you can see that minus clearly, but you'll be able to tell just from the number of electrons anyway. So fluorine, you've got 2 electrons there and then 7 electrons in the second shell. Two, 4, 6, 7. There we go. 9 electrons for fluorine versus 9 electrons for, or 10 electrons rather, for fluoride. Okay. 2, 4, 6, 8. Okay, there we go. And yeah, so fluoride ion bigger than the fluorine atom for the simple reason that if you add an electron to the to a shell that already has electrons in it, it's going to start, repelling the other electrons around it. It's going to demand its space, so to speak. So everybody just kind of moves out further so that the repulsions don't become too excessive and the atom stays stable, or I guess the ion stays stable. That's really all there is to it. You could also just think of it as simply the opposite of what happens with cations as you remove electrons. If removing electrons makes ions that are smaller than their original atoms, then adding them would make the ions bigger than their original atoms. Or you could do that ring around the rosy analogy, whatever helps you remember it. But yeah, the fluoride ion is isoelectronic with sodium ion and the neon atom. And I did not draw it to scale here, but if I had drawn it correctly, the fluoride ion would be bigger than neon. So my drawing is incorrect here, but the fluoride ion should be bigger than neon. And why is that? Because fluoride and neon both have 10 electrons, but neon has 10 protons pulling on those electrons, while fluoride only has 9. So I would expect fluoride to be bigger simply because same electrons, less protons than neon. Okay, so let me grab myself. I think it's in my other book. Let me go get that real quick for an example of an isoelectronic series. Let's see. Have to figure out which page it was on. Okay, I think I'm in the right chapter at least. Now just need to find... Where is... It's not there. If I can't find it, then maybe I'll just make up my own. Yeah, I think that's what I'm gonna do. Okay, I'm gonna make up my own. So I'm going to ask a question that's probably gonna be ridiculously hard in comparison to what you would normally be asked. but there's no preparation like over preparation, so don't complain about it. Let's rank the following. Rank the following species from, should we do largest to smallest or smallest to largest? Let's do from largest to smallest. From largest to smallest. And I guess you'll get to cheat a bit because I'll reuse some of the species that we just saw. So I want to do, let's see, sodium, magnesium, magnesium plus, magnesium 2 plus, neon, fluorine, fluoride, let's see, and oxygen, oxygen minus, and oxide, O2 minus. Yeah, let's rank those from largest to smallest. So my strategy for something like this is first to figure out how many shells each one has, and then start making comparisons within those smaller groups. So sodium atom is going to have 3 shells. The first 2 shells are filled, the third shell has 1 electron. Magnesium also going to have 3 shells. Magnesium plus is also going to have 3 shells. Magnesium plus is just minus 1 electron. It still has an electron out in the third shell. So magnesium plus is also going to have 3 shells. Magnesium 2 plus, you've removed both electrons from its third shell, so now it's on the second shell. Neon is a second shell. Fluorine, fluoride are second shells. Oxygen, O minus, O2 minus, all of those are second shell. Okay, so these first 3, which I coincidentally wrote right next to each other, all of those have 3 shells. So those 3 are definitely bigger than the remaining 7. Those 3 are definitely bigger than the remaining 7, so let's order those separately. Sodium, magnesium, and magnesium plus. Well, I know that magnesium is smaller than sodium because for neutral atoms, we know that the trend for the neutral atoms is for the atomic radius to decrease as you go to the right. And if you look at your periodic table, you will find that magnesium is to the right of sodium. So I know that sodium is bigger than magnesium. Now the question is, where do we put magnesium plus? Well, magnesium plus is isoelectronic with neutral sodium. Magnesium plus has 11 electrons and 12 protons. Sodium has 11 electrons and 11 protons. If they have the same number of electrons, but magnesium plus has more protons, then I would expect magnesium plus to be smaller than sodium. So it's going to be smaller than sodium. And I know it's going to be smaller than magnesium because same number of protons, but magnesium has less electrons for those protons to pull. We already established that cations are smaller than the atoms that they came from, so in fact magnesium plus is going to be smaller than plain old magnesium. I probably should have started by comparing magnesium plus to just plain magnesium. Anyway, that takes care of ranking the first 3, the biggest ones. Now let's take a look at the rest of these. So we've got magnesium 2+, neon, fluorine, fluoride, oxygen, O-, and O2-. All of them have 2 shells, but not all of them are isoelectronic. So magnesium 2+ has 10 electrons, neon has 10 electrons, fluoride has 10 electrons, and oxide has 10 electrons. So those go into a group. And then you've got fluorine and oxygen and O-, I guess, are just kind of like your wild cards. But let's see. So if I compare those 4, magnesium 2+ has the most protons, so it's going to be the smallest out of those 4. So Mg2+ is going to be the smallest out of the 4. Next would be neon, because it's got 10 protons for 10 electrons. So neon is bigger than magnesium 2+. Next we've got fluoride. Yeah, fluoride would be smaller than oxide because fluoride has 9 protons while oxide has 8. Less protons, bigger size. So fluoride is bigger than neon, and oxide is bigger than fluoride. Okay, and that just leaves us with the fluorine and oxygen and O-. So that leaves us with these 3. I know that O- is going to be bigger than O. Anions are generally bigger than the cations that, or not the cations, the neutral atoms that they came from. So O- is bigger than O. And oxygen is bigger than fluorine because oxygen is to the left of fluorine on the periodic table. Atomic size decreases as you go to the right, increases as you go to the left. Oxygen and fluorine are in the same row. With oxygen to the left of fluorine, oxygen would be bigger as a neutral atom and even bigger once you've added an electron to it. Okay, now the question is, where do these 3 fit among these 4? So that's the ridiculous part of this question that I was referring to earlier. They wouldn't really ask you something this intense, but it's not impossible to figure out. It's not impossible to figure out. So let's see. O- is definitely smaller than O2-, but is it bigger or smaller than F-? Let's compare. So F- and O- compare like F and O. F- and O- are just F and O plus 1 electron. So if oxygen in its neutral state is bigger than fluorine in its neutral state, then oxygen with 1 more electron should still be bigger than fluorine with 1 more electron. So I know this O- goes somewhere here between the oxide and the fluoride. Okay, what about regular oxygen? So regular oxygen would have a total of 8 electrons for 8 protons. Let me think. So really the question is fluoride bigger than oxygen? Oxygen is bigger than fluorine, and fluoride is bigger than fluorine, but which of these 2 is bigger? Because I already know fluorine is bigger than neon, so that goes there. Let's see, on what basis would I compare oxygen and F-? Well, let's look at their electron and proton counts. So oxygen has 8 protons, 8 electrons, 8p and 8e. Fluoride has, let's see, it would be 9 protons and 10 electrons. So, 8 versus 8 compared with 9 versus 10. I think 8 protons pulling 8 electrons will do a better job than 9 protons pulling 10 electrons, so I would imagine the neutral oxygen to be smaller. I would expect the neutral oxygen to be smaller, just on the basis of electron-proton ratios. So I believe now I have everything I need to get the complete ordering. So it should be sodium is the biggest, then magnesium plus, then O2 minus, then O minus, then F minus, then O, then F, then Ne, and finally Mg2 plus. Okay, there we go. That wasn't so bad. I'm sure some people are going to crucify me in the comments for that one anyway. So much for the spirit of learning. But yeah, with that, I think we can say that we've covered everything there is to be covered when it comes to ionic size. If you want to pick out your isoelectronic series, I guess there it is. So this, again, is an example of an isoelectronic series. Just to reiterate that point, they have the same number of electrons but differing numbers of protons. Okay. And yeah, away we go. So next up is ionization energy. Next up is ionization energy. So what is ionization energy exactly? Ionization energy is defined as that's a bad looking Y. Ionization energy is defined as the energy required to remove an electron from an atom or an ion. To remove an electron from, that's not how you spell from an atom or ion in the gas phase. So, if I wanted to do the following, I won't call it a reaction, but a process. If I wanted to do the following process, if I took a metal sodium and I turned it into a gas, I heated it up to the point where it transformed from solid to liquid to gas, and then I added even more heat, or I added energy in the form of electricity or light or whatever form of energy you're using. Then I could turn it into sodium ion with 1 electron removed. It's still in the gas phase, and you'd also have an electron that was released. And the energy required to accomplish this would be called the ionization energy. So you could say sodium gas plus ionization energy gives you sodium ion gas plus an electron. So you can think of it as having an implied plus ionization energy on the reactant side. But yeah, that's what ionization energy is. And you can ionize multiple times because most atoms, except for hydrogen, have multiple electrons. So you could take this sodium ion gas and add even more energy to it and eject another electron from it. So now you've got an electron with a positive 2 charge. Not something we encounter often in nature. In fact, I don't think we ever encounter this in nature, but it is something that you can do in the lab. You could just keep on firing energy at this thing and causing it to lose as many electrons as you want, or as many as you can afford to before the electricity bill comes in. So yeah, not only do you have one ionization energy, in fact you have multiple successive ionization energies. So we have to draw a distinction between first ionization energies, first IEs, and successive IEs. So two different patterns we want to look at. First, let's look at the pattern for first ionization energies, because that's the one that actually has a trend across the periodic table. So here is a table of first ionization energies for several elements. So if you look at the numbers, you notice, for example, to ionize hydrogen, to remove an electron from it, would cost, I think that's, kilojoules per mole. It would cost you 1,310 kilojoules for every mole of hydrogen that you want to ionize. For helium, the cost is higher. Then you go to lithium, the cost drops from helium. Then you go to beryllium, cost is higher. You go to boron, cost is actually lower. Carbon, cost is higher. Nitrogen, cost is higher. Oxygen, cost is a little lower. Fluorine, cost is higher. Neon, cost is higher. So for the most part, it looks like the ionization energy goes up as you go to the right. There are a couple of exceptions, as you can see, but for the most part, ionization energy seems to increase as you go to the right. What about if we go up and down? So if I go down the first column, we've got hydrogen is 1310, lithium is 520, sodium is 490, potassium is 420, rubidium is 400, cesium is 380, and francium is radioactive, so I guess they weren't able to determine an ionization energy for it. Or the authors of this book just didn't do enough research. Not the most crucial detail, so I don't blame them for it. Anyway, we can clearly see what the pattern is going down a column. The first ionization energy decreases as you go down a column. Okay. So, yeah, ionization energy goes up as you go up a column and goes up as you go to the right. I wonder if it's related to some other pattern that seems to change in the same way as you go up and to the right. In fact, we can relate first ionization energies directly to atomic size. First ionization energies can be related directly to atomic size. You see, the ease with which you can remove an electron depends on how close or far away that electron is from the nucleus. Electrons farther from the nucleus are easier to remove. Electrons farther from the nucleus are easier to remove. They're farther away from the attractive pull of the protons, so they don't experience as much of a pull. If you know your physics and you know Coulomb's law, you know that the strength of the electrostatic force is inversely proportional to the square of the distance between the charges. So the farther the charges are, the weaker their attraction. Electrons farther from the nucleus are easier to remove. Or, I guess, in terms of that concept of penetration, electrons with less penetration are easier to remove. Easier to remove means requiring less energy to remove. So, I guess I can switch that period to a comma. Thus, they require less ionization energy. Thus, they require less ionization energy. And there we have it. So if you remember the trend for atomic size and ionic size, then you can make sense of the trend for first ionization energy. Bigger atoms are expected to have lower ionization energies. Smaller atoms are expected to have higher ionization energies. So highest ionization energies occur as you go up and to the right, and smallest sizes along the periodic table also occur as you go up and to the right. Remember that. Remember what happens as you go up and right. I suppose you could also remember it both ways, up and right and left and down, but in my experience that tends to be too confusing and it's too much to remember. So for me personally, I would recommend just remembering the up and right patterns for all of the periodic properties that we're studying. Just remember what happens as you go up and right. Don't try to memorize it both ways. I think it was the same advice I gave for oxidation and reduction when we covered that stuff. I said memorize the definition of oxidation and just remember that reduction is the opposite of it, rather than trying to memorize both, because your memories will get mixed up and you'll confuse yourself and you'll be wondering if you answered correctly on your exam, and nobody wants to be in that situation. Okay, what else was I going to say here? So electrons farther from the nucleus are easier to remove, thus require less ionization energy. That connects the trend in first ionization energies to atomic size. Okay, what about successive ionization energies? So for successive ionization energies, I think it'll help to look at the following graphic, and maybe we can learn something from it. Okay, so here we've got the successive ionization energies for potassium, calcium, scandium, gallium, and germanium. Let's take a look at potassium. So its first ionization energy, the first electron removed, only costs you 418.8 kilojoules per mole. Then we notice that the second ionization energy is much higher. It's almost, well, actually more than 6 times as much. Maybe more than 7 times as much if my math is right. So yeah, there was a drastic increase in ionization energy. The next electron removed is not so easy to remove. The third electron for potassium is even harder to remove. The fourth electron is even harder to remove. And yeah, so every next electron you remove is going to cost you more than the one before it. And why on earth would that be the case? Well, if you think about it, as you remove electrons, there are two different things that are happening. One, you're increasing the ratio of protons to electrons. If there's more protons than electrons, then overall the protons are going to win it out and have the stronger pull on however many electrons are remaining. But there's another factor that comes into play here, which is the distances of those electrons from the protons. For potassium, the first electron you remove is in the fourth shell. But after that, after you remove the only electron you had in the fourth shell, the next electron you have to remove is in the third shell. It's a whole shell closer to the nucleus, so the nucleus has a much tighter grip on it. And that's why you see such a drastic change in ionization energy between the first and second electrons of potassium. Meanwhile, the changes between the second and third, third and fourth, fourth and fifth are still big, but kind of consistent with each other. Meanwhile, if we look at calcium, first ionization energy is decent. Second ionization energy is also relatively small. Third ionization energy, now you're removing an electron from the third shell. If you've removed the first two electrons of calcium, you've emptied out the fourth shell. So now you're on to removing electrons from the third shell, so you do notice a big jump in ionization energy all of a sudden. So if I were to give you a couple of unknown elements and I gave you their successive ionization energies, and I asked you to determine what their ionic charge would be, I would expect you to be able to figure it out, because you just look for where a large spike in ionization energy happens, and that tells you that you've emptied out a shell and you're moving on to electrons that are even deeper into the atom. But yeah, so that's successive ionization energies. Every ionization energy is greater than the one that came before it, but it's a much more drastic change between the last electron of a shell and the first electron of the next shell inside. I don't know if that statement made any sense, but maybe I'll try to illustrate it. So potassium, I guess I'll draw it here. I'll just draw a plus for the nucleus, and I've been using green for my orbits this whole time. Let's switch colors from that. So first shell, second shell, third shell, fourth shell. So yeah, this electron out here in the fourth shell is the easiest to remove, so you peel it away with a little bit of energy, and then the next electron you need to remove from potassium would be closer, would be harder to pull out. How many electrons are in there? Let's see, potassium is element number 19, so 2, 4, 6, 8, 10. And I guess I just have 8 there. Yeah, so I think with that illustration it's pretty easy to see what's going on. Okay, so that's ionization energy. Let me see. I guess our next trend is, you can think of it as the opposite of ionization energy, but it's not quite the opposite of ionization energy. So our next trend is electron affinity. Electron affinity. So what is it? It's the energy associated. It's the energy associated. Some people define it as the energy released. Yeah, I guess I'll define it as the energy released. The energy released when adding an electron to an atom or ion. Okay. Energy released when adding an electron to an atom and ion. Problem with this is you don't always release energy when adding an electron to an atom or ion. Sometimes it actually requires energy to shove an electron into an atom or ion. So, yeah, that definition isn't that good, but it gets worse. I hate this periodic trend because it's not so much that I hate it in itself, I just hate the way that chemists treat it. I hate the fact that it's recognized as a trend when there is no real trend. And if you want to know what I mean, just wait until I pull up the next graphic. But anyway, oh, I forgot. Just like ionization energy, this has to occur in the gas phase. And if you're wondering why it's so important for it to happen in the gas phase, I don't know the official reason, but I can guess. If I tried to ionize solid sodium by heating, for example, then what would happen? Well, I could measure out the amount of heat that I used, but what if some of that heat went into melting the sodium and changing it from the solid state to the liquid state, or from the liquid to the gas? So I'm not saying this is the official reason, but it's my best guess, and I think it's a very reasonable guess, is that when sodium's already in the gas phase, you can practically guarantee that the heat is going to ionizing the sodium, or whatever atom it is. You can practically guarantee when it's in the gas phase that the heat is going to ionization and not anything else. But yeah, that's my best guess as to why it's so important for it to be in the gas phase. But outside of that, I don't know the official reason. That's just my best guess, and again, I think it's a very reasonable guess. Some people might complain that I'm stating my guess when I'm not even sure, but I think that's the scientific spirit. I think it's important to show people, that you can think about things logically. You can try to figure out the reason on your own rather than just accept it from the authorities. Because that's not really critical thinking. And if Einstein listened to the authorities during his time, then we probably wouldn't have half of the inventions that we have today. So yeah, the true spirit of science is one that is non-conformist. Don't always listen to what the authorities have to say. Don't always obsess over being right according to the textbook or the teacher. Sometimes your common sense, even if it flies in the face of, what's the word I'm looking for? Orthodoxy. Sometimes your reasoning might actually be right, and you might be able to help revolutionize science. Thank you for coming to my TED Talk. I think that's how people use that phrase, or do they use it more sarcastically? I don't know. Anyway, back to electron affinity. So I wanted to do an example of it. Let's say we've got fluorine gas, monatomic fluorine gas, and I want to shove an electron into it. So I get the fluoride ion, and maybe, probably, it'll release energy. The delta H will be negative. But since electron affinity is defined as the energy released, it'll just be the magnitude of that. Anyway, yeah, electron affinity. So this, you could call it the first electron affinity of fluoride. And yes, the same way that we had successive ionization energies, we also have successive electron affinities. You could take this fluoride ion now and add the next electron to it to make this weird -2 fluoride ion. And that would be the second ionization energy. So just like, or did I say ionization energy? Electron affinity. It would be the second electron affinity. So yeah, just as with ionization energies, you can have successive electron affinities as well. We don't really dig into that because electron affinities are messy and not as predictable as your chemistry teacher might pretend that it is. So let's take a look at the following for electron affinities. Here we go. So let's see, what happens as we go up and to the right? They say that electron affinity is supposed to increase as you go up and to the right. So those are negative values, but again, electron affinity is supposed to be defined as the energy released. So the more negative they are, the higher the electron affinity. It's all to do with the definition. It's defined as the energy released, so the more negative values are the higher electron affinities, higher amounts of energy released. So yeah, as you go up and to the right, the claim is that the electron affinity goes up. Well, kind of, but not really. Look at the first column. We've got, starting from the bottom left and working our way up, we've got cesium at -45, rubidium at -46, potassium at -48, sodium at -53, lithium at -60, hydrogen at -72. So it does seem to be going up a little bit, but let me see, where was the one that stood out to me? Okay, no, actually the first column is fine. The first column does show the trend, I guess. Then where was the discrepancy that I noticed? Well, I guess you can see it in the second column, because in the second column you've got the same thing going on, but with positive values, so it's kind of reversed. So in fact, since barium down there at the bottom is the least positive, it's a +50, then it would be the same as being the most negative. Then again, maybe we shouldn't take those into account because those are all starred in the second column, and the star apparently represents a calculated value. Don't know how accurate the calculation is, but it's calculated and not measured, so I wouldn't trust it too much. If we look at the second row, specifically if you look to the right, boron, carbon, nitrogen, oxygen, fluorine, neon. So boron to carbon, I see an increase in electron affinity. Then you go to nitrogen and suddenly the electron affinity decreases. Then it goes back to increasing again when you go to oxygen, and it increases again when you go to fluorine. And you would think, since fluorine is closer to the top right, that it would have the highest electron affinity out of all of the atoms. But no, if you look below it, chlorine has more electron affinity than fluorine. And bromine, even though it has less electron affinity than chlorine, seems to still have more electron affinity than fluorine. So I fail to see where the trend is supposed to be. I mean, I guess you can say it's kind of there if you ignore a couple atoms, but it's not just a couple atoms you're ignoring here. It's like you're ignoring one atom out of every 3. And yeah, I just don't buy the whole idea that it's a trend, but it is what it is. What you need to remember from this is greater electron affinity occurs when you go up a column and to the right across a row. The changes as you go up a column are more drastic than the changes as you go to the right, in general. But as you saw from that chart, it's only generally true, and even then that's kind of stretching it. So let's see, the reasoning for why electron affinity increases as you go up a column. Well, that's easy. If you go up a column, then the atoms or ions are smaller. And if they're smaller, then they're probably better at holding on to electrons. If you add an electron to a small atom versus adding an electron to a big atom is really good at losing electrons, so you could reason that it's not going to be very good at grabbing new electrons. But smaller atoms, you would expect then, would be the opposite. They'd be better at accepting new electrons since they're worse at losing electrons. And of course, same logic applies as you go to the right, because the sizes decrease, but the decrease in size as you go to the right is less drastic than the decrease in size as you go up. And so you see a similar pattern with electron affinities. As you go to the right, the increase in electron affinity is less drastic than when going up. That's really all you need to remember as far as electron affinity is concerned. And actually, you might also need to remember that electron affinity is associated with an equation like this. In fact, you will need to remember it because later on, I think maybe 2 videos from now, or will it be 3? I'm not sure. A couple videos from now, we'll be doing something called the Born-Haber cycle to determine something called lattice energy, which will involve calculations that involve adding and or subtracting ionization energies and electron affinities. It'll be very, very similar to the Hess's law problems that we did for thermochemistry, where you take a bunch of equations and add them up to get some overall equation. But now I'm straying too far from our main topics. Let me see. So I guess next up is to describe something called metallic character before I dig into electronegativity. Metallic character, and this is going to be really quick. So metallic character isn't really a thing that, we quantify in chemistry. We could if we wanted to, but metallic character is kind of associated with all of the trends that we just covered. So we noticed that the bottom left of the periodic table is very different from the top right of the periodic table, and guess what types of substances we have on the bottom left versus the top right of the periodic table? Metals versus nonmetals. So you could say that having low ionization energies, having large atomic size, having did I already say electron affinities? Having low electron affinities and low ionization energies and large atomic size, all of those seem to be properties that are associated with metals. We said a long time ago that metals are better at losing electrons while nonmetals are better at gaining them. So it's easy to see why the elements in the top right, the nonmetals, are not going to be so good at losing electrons. We just explained how their first ionization energies are going to be really, really high due to their small size, and why their electron affinities, on the other hand, will also be high, because if it requires a lot of energy to lose electrons, then you stand to gain a lot of energy by adding them to nonmetals. So you could say that as you go up the periodic table and to the right, metallic character, the quality of being metal, decreases. So if you're ever asked which of these atoms do you expect to be more metallic, then really it's just a matter of following the periodic table up and to the right. The further up and the further right you go, the less metallic you become. But yeah, so that's metallic character. Now then, electronegativity. Electronegativity. Maybe I should do this on a separate sheet. Yeah, let's do that. Electronegativity. I'm actually not sure how to define this. Maybe I should check the definition in the book and go with that, because I'm not sure how I want to define it off the top of my head. Electronegativity, I guess it's... Oh, wait, I know how I want to define it. Electronegativity is how well an atom attracts electrons in a bond. How well an atom attracts electrons in a bond. So if I were to draw a couple of different molecules, such as the water molecule, which looks like this, and the ammonia molecule, which looks like this. A while back I described these as being covalent bonds. Covalent bonds. And what we're told by our teachers about covalent bonds is that they're bonds formed by atoms that just agree to share electrons, but that's not really what's going on. The atoms aren't really sharing the electrons in the bonds. It's more like this tug of war that has no clear winner, and so they stick together. The atoms stick together because no one can steal the electrons off the other outright. So yeah, it's not really sharing, it's more of an endless competition for electrons. And because it's not sharing, it's not always fair. Even though there's no clear winner, sometimes you can tell who has the advantage. So it turns out when you study the water molecule that the two electrons that are being shared, quote-unquote, shared between hydrogen and oxygen, the two electrons in this bond, they tend to hang around the oxygen more than they do around the hydrogen. The oxygen is better at pulling the bonding electrons towards itself than hydrogen is. Hydrogen still gets to, what's the word? Experience the state of having two electrons, but not as much as it could. And let's see, same case for nitrogen. Nitrogen is also pretty good at pulling the bonding electrons more towards itself and less towards the hydrogen. So what determines the strength of this pull is something called electronegativity. If oxygen is better than hydrogen at pulling the electrons in this bond, then it's said to have a higher electronegativity than hydrogen. Nitrogen, by the same reasoning, has a higher electronegativity than hydrogen. So your ability to pull electrons in a bond towards yourself is going to depend on size, just like everything else. I told you that all the periodic trends would be based on atomic size, and I wasn't kidding. The smaller the atom, the better it is at pulling electrons in a bond towards itself. And so, with the exception of the noble gases, if you leave the noble gases out of it, the most electronegative atom is fluorine. Fluorine has the highest electronegativity of all the atoms according to the Pauling scale for electronegativity. Fluorine is the only atom with an electronegativity of 4, and everything else is less than that. So highest electronegativity. Did I spell that right? Yeah. Okay. So fluorine has the highest electronegativity, which sits at 4.0. It's a bit of a crude calculation, but there is an electronegativity scale. Apparently it can be done through measurements. For the longest time I thought it was just rankings and not precise measurements, but yeah, these are measured values. They're just not measured as precisely as I would hope. So anything that we study based on electronegativity, anything we conclude on the basis of electronegativity, we're going to have to remember that we're drawing those conclusions based on guidelines and not strict rules. If you want rules, go study physics. So yeah, that chart shows you that electronegativity increases to the right and decreases down, or in other words, it increases as you go up and right, just like all of our other periodic trends. Just remember the up and right pattern. So let's see, atomic size increases up and right, or no, decreases, my bad. So ionization energy and electron affinity, first ionization energy and first electron affinity to be specific, those increase as you go up and to the right, and so does electronegativity. So all three of those increase as you go up and right. And atomic size decreases as you go up and right. So three things that increase, one thing that decreases as you go up and right. And ionic size isn't really something you can read off the periodic table, because the periodic table covers the atoms and not the ions. So for those, you just have to compare to the nearest atom. But we already did an intense exercise in that. So yeah, fluorine sits at 4.0, oxygen is at 3.5, nitrogen is at 3.0, if I'm reading that right. It looks smaller on my screen than it does on yours, probably. Chlorine is also a 3.0, but we typically regard fluorine, oxygen, and nitrogen as being the most electronegative atoms. We don't really think of chlorine as being equal to nitrogen in electronegativity. But yeah, based on differences in electronegativity, we can actually predict whether bonds are going to be ionic or covalent, and in fact, we can also predict whether or not bonds are going to be polar. So if I go back to what I drew here, since there's a big difference in electronegativity between oxygen and hydrogen, and between nitrogen and hydrogen, we can say that the bond between oxygen and hydrogen here is polar. This is a polar bond. Polar bond. And what do I mean by polar? Well, what I mean by polar is that you create two poles, a positive pole and a negative pole. Think of how magnets have a north pole and a south pole. Same thing with electricity. If you have a net positive charge in one place and a net negative charge on the other end, then you have an electric dipole, kind of like a bar magnet. It's got a positive pole and a negative pole. So, since oxygen has the higher electronegativity compared to nitrogen, I didn't point it out when I had the table up just now, but hydrogen has an electronegativity of 2.1, oxygen is 3.5, 3.5 and 2.1 is a difference of 1.4, which is considered pretty big. So oxygen pulls the electrons in the bond more towards itself, and so the oxygen, it doesn't steal the electrons, so it doesn't, it doesn't become an ion. I shouldn't be using orange here. It doesn't quite become an ion, but it does develop a kind of negative charge. A partial negative charge is what we call it. And so the hydrogen doesn't quite lose the electrons, it develops a partial positive charge. And yeah, we use that symbol delta, so if you want to look at how to write it, basically think of it like an S with a closed loop is probably how I would describe it. And then, put in a plus or a minus, depending on whether you want to represent a partial positive or a partial negative. But anyway, same deal with nitrogen. Since it's got more electronegativity than hydrogen, it's going to develop a partial negative charge, and hydrogen is going to develop a partial positive charge. On the other hand, if the difference in electronegativity is really large, then a covalent bond may not form at all. You might actually get an ionic bond. This would happen between something with really high electronegativity and something with really low electronegativity, such as sodium and chlorine. Sodium doesn't share with chlorine, it just loses an electron to chlorine. Sodium loses one electron to chlorine, and what keeps them together then is the electrostatic attractions, the attraction between oppositely charged objects. But yeah, chlorine never gives that electron back. They just both hold on to the electrons that they have. Chlorine holds on to the electron it stole from sodium, and sodium never tries to grab back its electron, or maybe it tries but fails miserably. And you can explain this with the large difference in electronegativity between sodium and chlorine. Sodium has an electronegativity of 0.9, while chlorine has an electronegativity of 3.0. That's a different, 3.0. So yeah, that's a difference of 2.1. That's a difference of 2.1, which is considered pretty big, pretty drastic. So, in light of this, we have the following set of guidelines, and depending on who you ask, these guidelines change. I've heard different numbers from different people. So again, remember, this is chemistry. In chemistry, there are patterns with lots of exceptions. There aren't any rules. So don't take these to be strict rules, just take them more as a guideline than anything else. If there's little to no difference in electronegativity, so according to that mini chart on the right, if the electronegativity difference is less than 0.4, you could consider it a pure covalent bond. You could consider the sharing to be pretty much equal when it comes to the electrons in the bond, and you wouldn't expect any partial charges to develop. If you have an intermediate difference in electronegativity, so somewhere between 0.4 and 1.8, again, those numbers are not set in stone, then you might have a polar covalent bond, and if the difference in electronegativity is greater than 1.8, then you probably have an ionic bond. You're probably dealing with an ionic substance. So yeah, again, those rules are not set in stone. I know some people say 1.7 instead of 1.8, and some people say 1.9, and some people instead of 0.4, they'll say 0.5 or something like that. So those cutoffs are not set in stone. They're guidelines. I can't stress that enough. In chemistry, the only way to know for sure is to do the experiment in the lab and measure. But these are just guidelines to help you make predictions. Okay, what do I have next? So we've talked about electronegativity, we've talked about metallic character and all the trends. There's something I want to introduce now. We'll dig into it some more later, but I want to introduce it right now since we've covered ionization energy. Actually, you know what? I will save it for later. Never mind. Let's just go ahead and move on to Lewis symbols. Let's go ahead and move on to Lewis symbols. You noticed I started drawing some molecules. It's time to learn how to draw. So you may remember in the previous video, and I think I mentioned it towards the beginning of this video too, you may remember the concept of valence electrons versus core electrons. Valence electrons are electrons in the outermost shell. So valence electrons are going to be the electrons you need to take into consideration when drawing Lewis symbols. Valence electrons are the outermost electrons. They're in the highest energy levels. They're in the highest N value in terms of shells. Outermost electrons of an atom or ion. Okay, so valence electrons, very, very important when trying to determine the Lewis symbol for an element or an ion. So a Lewis symbol is simply the symbol of the element surrounded by dots that correspond to the number of valence electrons that that atom has. So let me draw the Lewis symbols for the first couple atoms. Actually, no, not the first couple atoms. Let's do all the atoms of the third row. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay, if we were to look at the electron configurations of these, sodium is neon, a bunch of core electrons, followed by 3s1. So its valence shell is the third shell, which contains only one electron in the s subshell. So I would simply draw one dot on sodium. Let me actually, divide these so I don't confuse the dots of one with the dots of another. So sodium has 1 electron in its outermost shell. Okay, magnesium. By the same logic, it's neon 3s2, so it's got 2 electrons total in its valence shell. Aluminum is going to be neon 3s2, 3p1. So 2 electrons in the s subshell plus 1 electron in the p subshell. So you've got a total of 3 electrons in the third shell, in the valence shell of aluminum. Okay, silicon is going to have 4 by the same reasoning. Phosphorus is going to have 5. So once you have more than 4, remember to follow this pattern. Just go, I guess, clockwise or counterclockwise, whatever you prefer, and go 1, 2, 3, 4, and then once you've had 4 single dots, that's when you start pairing your dots. So 5, I'm going to pair it with the first electron that I drew, with the first dot. Sulfur has 6, so 1, 2, 3, 4, 5, 6. If you like your symmetry, you could also draw sulfur like this. 1, 2, 3, 4, 5, 6. If you prefer your symmetry, this and this both are perfectly fine. Chlorine has 7, so 1, 2, 3, 4, 5, 6, 7. Argon has 8 electrons in its third shell, and I guess we're just going to have 4 pairs, so there they are. Okay, so 1 valence electron, 2, 3, 4, 5, 6, 7, 8. So that's valence electrons. What about this other concept known as valence? This is going to be important later. Valence. Valence is not the same as valence electrons. The valence of an atom is the number of unpaired valence electrons. The number of unpaired valence electrons. Know the difference between valence and valence electrons. It's not the same thing. The number of unpaired valence electrons. So valence electrons, I already counted 1, 2, 3, 4, 5, 6, 7, 8. And for the valences, sodium has 1 unpaired electron, so it's got a valence of 1. Magnesium has a valence of 2. Aluminum 3. Silicon 4. Phosphorus has 3 unpaired electrons, so it's got a valence of 3, not 5. It's got 5 valence electrons and a valence of 3. Sulfur has a valence of 2. Chlorine has a valence of 1. Argon has a valence of 0. Okay, so that's valence electrons versus valence, and there you go. Those are basic Lewis symbols for atoms. What about Lewis symbols for ions? The Lewis symbol for a cation, assuming you've removed all of its electrons, all of its valence electrons, will just be the symbol of that element. So if I remove an electron from sodium, then the Lewis symbol for the sodium ion is just this. That's it, nothing surrounding it. If, on the other hand, I want to draw the Lewis symbol for the sulfide ion, then I need to add 2 electrons to it. So I guess I'll do it here, since I already have a sulfur there. And I'll write a -2 there. And there you go. That's the Lewis symbol for the sulfide ion. So anions that get all 8 electrons to fill their, I wouldn't say outermost shell, but to fill their outermost 3s, not 3s, their outermost s and p subshells. It doesn't matter whether it's 3s or 4s or 5s, along with 3p, 4p, and 5p, or lost my train of thought again. What was I saying? Oh, right. So it doesn't matter what shell they're in. It doesn't matter how many electrons it takes to fill their outermost shell. What matters is how many electrons it takes to fill the outermost S and P subshells. So your Lewis symbol for an anion, once it's got all the electrons it can get, it should just be surrounded with 8 dots. And for a cation that has lost all the electrons it can lose normally, it should just be that ion without any dots surrounding it. Okay, so those are Lewis symbols, and they're all good and great, but they don't really represent compounds, so how do we represent compounds as opposed to individual atoms or ions? Let's take a look at ionic compounds. We usually don't draw Lewis structures for ionic compounds, but if you're trying to draw a compound, that's called a Lewis structure, not just a Lewis symbol. So for an ionic compound, let's say, for example, calcium chloride. Let's say I want to draw calcium chloride, CaCl2. Then I would have, let's see, calcium ion has 2 valence electrons normally, but to make the ion you need to remove those, so nothing around calcium. And then the chlorides, chlorine normally has 7 valence electrons around it. Add one more taken from calcium, and I guess I'll represent that with this color. So those 2 magenta colored electrons are electrons that were acquired from calcium. So there you go. Let's put in the minus sign so that we remind ourselves it's an ion. And there's the Lewis structure for calcium chloride. I guess you'd want to draw these a little bit closer to show that they're together. So don't put as much distance between them as I did. And in fact, you probably don't even need to write down the charges. I've seen people write it more like this. But yeah, Lewis structures for ionic compounds are not something you're asked to draw very often, so I wouldn't obsess over this too much. On the other hand, for molecular compounds and polyatomic ions, oh boy, now it's time to start having fun. So what we can see here from the Lewis symbols for anions is that you can't have more than 8 electrons surrounding an element, surrounding an atom. And that's kind of true for the most part, but we'll definitely see some exceptions to it. So this idea that most atoms are satisfied with being surrounded by 8 electrons is referred to as the octet rule. It's referred to as the octet rule. But we will definitely see exceptions to the octet rule. One exception I can bring up right now is hydrogen. Hydrogen normally has 1 electron in its outermost shell, which is its only shell, and its outermost shell can only hold 2 electrons at most. So if you were to give electrons to hydrogen, then it doesn't have the capacity to have 8 electrons surrounding it. So hydrogen is definitely an exception to the octet rule. Whenever hydrogen is even in the role of accepting electrons to begin with. Usually hydrogen's the one losing electrons. But I digress. Let's go ahead and dig into the rules for drawing Lewis structures. So the textbook has one set of rules, and other textbooks have had other sets of rules for drawing Lewis structures, but here's the set of rules that I just kind of intuitively put together, and it might match what you see in some textbooks, if they're good textbooks anyway. But here's my version of it. So whenever we want to draw Lewis structures, and I will illustrate these with examples, but first thing I do, step 1 for drawing Lewis structures for covalent compounds, for molecular compounds. My first rule is identify what's going to be your central atom. Identify the central atom. So this concept of a central atom, if it doesn't make sense to you, let's go back to the structures I drew for water and ammonia. So if I go back to, there it is. So if I look at my structure for water, and maybe I should redraw it down here so that we can see it more clearly, then here I think nobody would argue with me that oxygen is clearly the central atom here. It's kind of in the middle. It's the one that's holding everything else together. Nitrogen is the central atom for ammonia. Nitrogen is kind of at the center of everything, and it's holding on to the other atoms in the molecule. Okay, so identifying the central atom. How do we determine what the central atom is? Look for 3 things. First and foremost, look for highest valence, not valence electrons, highest valence. If you have a compound with multiple atoms, compare those atoms and determine which one has the highest valence. That one should be your central atom. What if I have more than one atom with the same valence that happens to be the highest valence? What if I have 2 atoms with a valence of 3, for example? Then the next thing, actually no, this isn't the first thing to look for. Hold on. My bad, this isn't it. First, look for, what's it called? The rarest, the least common atom. So in the cases of water and ammonia, for water you've got 1 oxygen and 2 hydrogens, so it wouldn't feel right for one of the hydrogens to be in the middle. You've got 1 oxygen, that one ought to be in the middle. Same thing with the nitrogen in ammonia. There's only 1 nitrogen versus 3 hydrogen, so it kind of intuitively makes sense that the 1 nitrogen should be the one that's propped up at the center. It just appeals to your sense of symmetry. And your sense of symmetry, your symmetrical intuition, if that's what you want to call it, is often, if not always, going to be right. But yeah, if you can't identify the rarest atom, if you have a compound like HCN, there's 1 hydrogen, 1 carbon, and 1 nitrogen. They're all equally rare since there's only 1 of each. In that case, you look for highest valence. Highest valence. And then if you still have a tie, the next thing you look for is largest size. So whichever one is the rarest, if they're equally rare, break the tie by comparing their valences. If they have equal valences, then pick whichever one of the 2 or 3 or however many atoms you're considering is the largest. Okay, so that takes care of rule number 1, identify the central atom, and of course draw it as the central atom. Rule number 2, or step number 2 I should say, create a single bond between, I guess I'll write it over there, between, yeah, I don't think it would have fit, between the central atom and each of the, as I like to call them, guest atoms. I like to think of the central atom as a host and all the other atoms as a guest. So I'm going to call them guest atoms. You can call them whatever you want, maybe surrounding atoms or something like that if you want to be highly technical about it. But I'm going to call them guest atoms. So create a single bond between the central atom and each of the guest atoms. Number 3, step 3, give each guest an octet. This will make more sense when we see an example, so don't freak out if you're not following. Give each guest atom an octet, with the exception of hydrogen, of course. With the exception of hydrogen and helium. I don't think you'll ever have to deal with helium, so give them each an octet except for hydrogen. Rule number 4, tally up valence electrons used versus valence electrons available. Again, this will make more sense when we start looking at examples. Tally up valence electrons used versus valence electrons, I guess I'll write it there, available. Step 5, place all leftover valence electrons on the central atom Step 6, if the central atom has less than an octet, if the central atom has less than an octet, take lone pairs, which I will define soon. Take lone pairs and create double, that's not how you spell double, double and or triple bonds to achieve an octet. And this rule actually has an exception that you just kind of have to know about, but we'll get to it when we get to it. We might get to it in this video, or we might get to it in the next video, because in the next video we're going to be drawing a lot of Lewis structures, so we don't have to do it all in one video. But yeah, so those are my 6 rules. Now let's go ahead and start illustrating them. So I think I have a couple of problems ready for that, if I'm not mistaken. Let me see. Okay, I have some Lewis symbol exercises, but I think those are going to be easy enough to do later, or just just show off for those who need practice. Structures, there we go. Okay, so it says write Lewis structures for the following. First we've got oxygen gas. First we have oxygen gas. So oxygen gas, if I go ahead and pick between the 2 oxygen atoms, which one is the rarest? Which one's the most unique? Well, the only choice is oxygen, so I'm going to put down one of my oxygens as the quote-unquote central atom. And then according to step 2, I need to create a single bond between the central atom and each of the guest atoms. Well, there's only one other atom, which is the other oxygen. So I'm going to create a single bond to it. And this single bond essentially represents 2 electrons. And those 2 electrons count towards both oxygens. Okay, then step 3 tells me to give each guest atom an octet. So I'm going to give this oxygen an octet by adding lone pairs. So lone pairs are the paired dots that we saw earlier in our Lewis symbols. Those are called lone pairs. Okay, 3 lone pairs plus the 2 electrons in the bond. This oxygen now has a total of 8 electrons in its vicinity. It has an octet. So that was step 3. Step 4, tally up valence electrons used versus valence electrons available. So far I've used 2, 4, 6, 8 electrons, 6 of which are in the form of lone pairs and 2 of which are in the form of a bonding pair. So that's 8 electrons used. How many electrons in total, how many valence electrons are available with oxygen gas? Well, I have 2 atoms of oxygen, and each oxygen atom has 6 valence electrons. So that's a total of 12 electrons available. 12 electrons available. Okay, that means we have 4 leftover electrons. What do we do with leftovers? Leftovers are not handled by guests. Leftovers are handled by hosts. Place all leftover valence electrons on the central atom. So place my 4 leftover electrons on this guy. Step 6. If the central atom has less than an octet, take lone pairs and create double and or triple bonds to achieve an octet. So This oxygen has 2, 4, 6 electrons in its vicinity. That's not 8. And less than 8 is not good. Sometimes you end up in cases where you have more than 8, and those are some exceptions that we'll see later. But less than 8, if you can turn it into 8, usually you should. So how do I turn this into 8 when I've already used all the electrons I have? Simple. Take the electrons that are already in a lone pair with one of your guest atoms and turn them into a bonding pair. So if I do that, then this oxygen will be left with 2 lone pairs, and this oxygen still has 2 lone pairs. And there's the original bonding pair, and there's also a second bonding pair. We've formed a double bond. So what's great about this is that the 2 electrons that this guest atom gave to form the bond, they still count towards the guest atom. If I were to draw circles illustrating the electrons that count towards this oxygen, or anything that fits within that circle, the electrons that count towards that other oxygen is anything in that circle. And since each bond contains 2 electrons, you've got 2, 4, 6, 8, but you've also got 2, 4, 6, 8. The guest atom didn't lose any electrons from its octet, but the host, the central atom, was able to achieve an octet for itself as well. Everybody's happy, holds hands, and sings Kumbaya and all that good stuff. So there you go. There's a simple illustration of how to follow those rules, but this does not take into account charge. Only difference if you have a polyatomic ion that's charged is when you're counting your available valence electrons, you also add or subtract enough electrons to create the appropriate charge. We'll see that when we get to it. Let's actually do some more of these. I'll do a couple more. So, okay, let's do H2CO. Let's do H2CO. And I guess I can do it on this same page. There's still plenty of space. H2CO. Okay, what's the rarest atom? I've got 2 hydrogens. I've got 1 carbon and 1 oxygen. So carbon and oxygen are equally rare. And next I look at valence. Carbon has a valence of 4, oxygen has a valence of 2. Remember the difference between valence and valence electrons. Carbon has more valence than oxygen, so it's going to be carbon. Carbon is my central atom. Single bond it to each of the guest atoms. And if you're worrying about what shape I should be drawing, that's going to be covered in the next video. So for now, you can just do whatever in terms of the shape. I'll try to be as symmetrical as I can be. But yeah, don't worry too much about getting the right shape this time around. We'll see how all that works in the next video. Where was I? Okay, so single bond to each guest atom. Give each guest an octet. Hydrogen is an exception. It doesn't need an octet because it can't hold an octet. So that only leaves oxygen. So I'm going to give it 3 lone pairs. That way it's got a total of 8 if you include the bond. Tally up electrons. So we've got, let's see, we've used 2, 4, 6, 8, 10, 12 electrons. 12 used. How many do we have? How many are available? So hydrogen brings in 1 electron each, so that's 2, plus, so that's 2 times 1, plus carbon brings in 4 valence electrons, plus oxygen brings in 6 valence electrons. So 2 plus 4 plus 6, that would be 12. So we've already used all of our available electrons. There are no leftovers to dump onto the central atom. So now we skip to the final step. If the central atom has less than an octet, which carbon does because it's only got 2, 4, 6 electrons surrounding it, then we need to consider double and or triple bonding. So I'm going to remove a lone pair from here and place it here. That way it still counts towards the oxygen, but now it also counts towards the carbon. And there you go. Now carbon and oxygen have octets. Hydrogen can't have an octet. Everything is satisfied. There you go. Okay, next, let's do let's do H3O plus, part F. That's the hydronium ion. We will see the hydronium ion a lot in the second semester material. That's going to be several videos from now, but it's coming. Hydronium, H3O plus. This is a polyatomic ion. Okay, so identifying the central atom, clearly it has to be oxygen. So we've got oxygen as our central atom. Bond 3 hydrogens to it. Through single bonds. Whether we get double or triple bonds remains to be determined. In fact, you shouldn't expect to get them with hydrogen, but that's another story for another time. So we've single bonded everything. Tally up electrons. We've used 6 so far. 6 used. How many are available? So we have 3 hydrogens, each with 1 valence electron, so that's 3 times 1, plus oxygen brings in 6. But overall, this polyatomic ion has a charge of positive 1, which means we've got 1 electron less than what these atoms would normally have in total. So minus 1 electron to create a positive 1 charge. Okay, so that's 3 plus 6 minus 1, 9 minus 1, which is 8. We've got 8 electrons available. So since we have 2 leftover electrons, leftovers are handled by the host, or the central atom in other words. So there we go. If the central atom has less than an octet, well, this one doesn't have less than an octet. It has an octet because 2, 4, 6, 8. There are 3 single bonds and 1 lone pair around the oxygen atom. So yes, the oxygen is surrounded by 8 electrons. It's already got enough. No need to do double or triple bonds, and even if there was a need, you wouldn't be able to do it because there are no lone pairs on any of the hydrogens that you could contribute to a double or triple bond. Okay, let's look at another one. Here's an anion, Bf4 minus. So that's part H, Bf4 minus. BF4 minus. I have no idea what that polyatomic ion is called. But BF4 minus. Okay, so central atom is clearly the boron. So connect it to 4 fluorines. Give each of the fluorines an octet. Tally up electrons used versus electrons available. So I've used 8, 16, 24, 32. 32 used. How many available? So boron would have, let's see, 3 valence electrons normally. So 3 valence electrons for boron, plus 4 times fluorine comes with 7 valence electrons each. And then the negative charge tells me that I have 1 extra electron on top of the ones that normally come with those atoms. So 3 plus 1 is 4. And then 4 plus 28 would be 32. So that's it. I've used all of my available electrons, no leftovers to dump onto boron. And boron already has an octet, 2, 4, 6, 8, so we're done. That's it. Okay. Let's see. We've got... I want to look at that last one of part 29, or problem 29, because I don't think I've encountered anything like that before. C2, 2 plus. C2, 2 plus. Can you guys see that? Let me push it up a bit. C2, 2 plus. Let's see what we've got. So carbon is the central, the central atom. Let's see. So bond it to the other carbon, give the other carbon an octet. Tally up electrons. So we have, let's see, 8 used so far. And how many available? Each carbon has a valence of 4. And each carbon has a valence of 4. So that's 2 times 4. And then the positive 2 charge tells me that we're missing 2 electrons. Or we have 2 electrons less than what we normally would have. So that's 8 minus 2 is 6 available. Okay, I've never encountered a situation like this one before. Eight used, but only 6 available. Well, we can't really form octets with only 6 electrons. I'm wondering if they actually meant for this to be a 2 minus, and they accidentally typed 2 plus when writing the problem, because you can't make octets with just 6 electrons. Either that, or they meant for us to come up with this structure, which still doesn't give either carbon an octet, but it is the most even way to share the electrons. Yeah, I'm willing to bet this was supposed to be a negative 2 charge. And if that's the case, then if that's a minus, then that's plus 2 additional electrons, giving us 10 available electrons, giving you 2 to dump onto the central carbon in terms of leftover electrons. Central carbon would not have an octet, so take one lone pair, form a double bond. Central carbon would still not have an octet. It would go up to 6. So take another lone pair and form a triple bond. So we would end up with lone pair, C, triple bond, C, lone pair, like that. Oh, and by the way, something I've been forgetting to do with these charged species, I really should be putting them in brackets. Whenever you're dealing with a polyatomic ion, you should put it in brackets and show the overall charge of that polyatomic ion. So take Bf4 minus as well and put that in brackets and put a -1 charge on it, and take this thing in brackets and put a -2 charge on it, or a 2 minus rather. I will probably forget that a lot. But yeah, remember to put brackets around polyatomic ions once you've drawn their Lewis structures and show the charge. Show the overall charge. Okay. Let me see. I think 30 part A would be a good example. CLF3. Okay, so let's move on to a new sheet. And I think I'll do one more example after this one, and then we can talk about the concepts of formal charge and resonance structures. Okay, so it was CLF3, neutral. CLF3. Okay, so we've got chlorine clearly is going to be the central atom here. Okay, 3 fluorines. Give each of them an octet. Tally up electrons. I've used 8, 16, 24 electrons so far. So 24 used. How many do we have available? Well, chlorine has a valence of 7, and fluorine, or not a valence, has 7 valence electrons, and fluorine has 7 valence electrons. So that's 4 times 7 is 28 total valence electrons. We don't have to add or subtract anything since the charge is 0. So we've got 4 leftover electrons. They need to go onto the central atom. Leftovers are handled by the central atom, so there's 2, there's 4. We need to put them on as pairs. Unless they're an odd number. If they're an odd number, first of all, you shouldn't expect to get an odd number, but if you do have an odd number, then if you have to choose between 2 different atoms, which one is going to get the extra electron and which one is going to have an incomplete pair, the one with the incomplete pair should be the one with lower electronegativity. I doubt you're going to need to remember that because they rarely, if ever, ask that sort of question. But there it is in case you were wondering. So let's see. Leftover electrons dumped onto the central atom, and the central atom has more than an octet, so there's nothing we can do about this. We definitely don't want to double or triple bond here, because then the central atom would have even more electrons around it, and it's already past an octet, so we just leave it as it is. Okay, so that's CLF3. Okay, and one more. Let's do... Actually, I don't want to do any of these. Let me do one that'll actually help us transition into our next topic. Let me do one that'll actually help us transition into our next topic. So let's do the nitrate ion. Let's do the nitrate ion. NO3 minus. The nitrate ion is going to have nitrogen at the center, since there's only one of it. So 3 oxygens are going to be bonded to it. Give each oxygen an octet. Tally up electrons. So we've used 8, 16, 24. We've used 24 electrons. How many do we have available? So nitrogen brings in 5, and each of the 3 oxygens brings in 6, and a charge of -1 tells us that we've got 1 electron more on top of what the atoms normally bring to the table. So 5 plus 18 plus 1. Well, 5 plus 1 is 6. So 4 6s, that's 24. We've used all of our electrons. But nitrogen has less than an octet, so we remove a lone pair from one of the guest atoms and make a double bond. But here's an interesting question. Which oxygen do we remove from? Well, in this case, it's possible to remove from any one. So in fact, you've got 3 possible structures for the nitrate ion. You've got 3 possible structures for the nitrate ion. Or I guess 4, because technically this counts as a structure even though it violates the octet rule for nitrogen. But we've got 3 possible structures aside from this one. We've got 3 possible structures for the nitrate ion. We've got one that looks like this. We have one that looks like, I probably should have drawn it smaller. We have one that looks like this. And we have one that looks like this. Okay, and let me bracket each of those. So that's a -1 charge. That has a -1 charge. And that has a -1 charge. All of them should have a -1 charge overall. But yeah, you have 3 different resonance structures, or 4 if you want to count this one, though it's a really bad one. But yeah, we've got 3 different resonance structures for the nitrate ion. When you have multiple possible Lewis structures with different placements of the double or triple bonds, we call those resonance structures. In fact, it's not exclusively about double and triple bonds, but that's complicated stuff that you'll learn more about if you ever take organic chemistry in college. For now, just think of resonance structures as having to do with the locations of double and triple bonds. though it isn't just that. You will learn more about it in college if you choose to pursue chemistry further. Anyway, these three structures are considered to be equivalent to each other. They are equally representative of what the real nitrate ion looks like. But the real nitrate ion, we have to bear in mind, is not going to care how we draw it. Lewis structures are just a convenient tool for us humans to understand how atoms and molecules and ions and polyatomic ions work. But as you can see, Lewis structures are not foolproof. In fact, the truth is that we would have to kind of blend these three together to get an accurate representation of the real nitrate ion. The real nitrate ion would be something like, well, it would be, you'd have the nitrogen at the center, of course, and you'd still have the three oxygens around. And instead of two single bonds and one double bond, you'd have 3 1 1/3 bonds, if that makes any sense. However, I mean, if you look at that, can you clearly tell that it's a third? Probably not, and with someone else's handwriting, it might be even harder to tell that that's supposed to be a third and not a fourth or 2/5 or something like that. So the fact of the matter is, we just don't have a clever way of showing a 1 1/3 bond. We don't have a way of showing that those 2 electrons there are actually kind of shared across everywhere, across the whole entire ion. And how many lone pairs would we still have in that case? I'm not even sure. Yeah, I'm not going to bother thinking about it. It's not like we actually have a good way of representing the nitrate ion. But yeah, so these are, once again, they're called resonance structures. And resonance structures, we can compare them to figure out which resonance structures are probably good representatives of what the actual molecule or ion is, and which ones are bad representatives. And then once we see what all the resonance structures are, you just kind of mentally blend them together and use your imagination a bit to picture what the real molecule or ion is like. So how do we determine what's a good resonance structure and what's a bad one? Introducing the concept of formal charge. Introducing the concept of formal charge. So formal charge, there's this long, clunky equation that they put in textbooks, and I hate it because, I don't know, I guess I'm more of a visual thinker, and I think it's very easy to remember how to calculate formal charge visually. It's much easier than memorizing the clunky equation that they give us. But let me put that equation up in front of you. Where is it? Formal charge, there we go. So it says formal charge equals the number of valence shell electrons of the free atom, or the neutral atom in other words. I don't know why they used the word free there. But the number of valence electrons that the atom normally has, minus the number of lone pair electrons surrounding that atom, minus half of the number of bonding electrons. Minus half of the number of bonding electrons. So, yeah, I think that's too much to remember, and even if you remember it, it's too much to write out. So, here's what I propose instead for calculating formal charge. Draw a tight circle around each atom in a Lewis structure such that the circle cuts halfway through any bonds that that atom is connected to. So for example, if I wanted to do it for water, here's what the Lewis structure for water looks like. We've seen it several times by this point. So I would draw a circle around the hydrogen that cuts halfway through the bond that's connected to hydrogen. Same thing over there for the other hydrogen. And for the oxygen, I'll do the same thing, but I'll use a different color. So draw a circle for oxygen that cuts about halfway through each bond connected to oxygen, but encircles all of the lone pairs. And here's what you do to calculate formal charge according to my method. Basically, just take valence electrons of that atom, valence electrons, minus circled electrons. It's that simple. Circled electrons. That's all you need to do. Valence electrons minus circled electrons. And remember, at the ends of each bond, imagine each bond as having 2 electrons on its ends. Not because that's realistically how the electrons exist between the hydrogen and the oxygen, but because it just makes it easier to calculate formal charge via this method. So let's see. Hydrogen has 1 valence electron. Normal hydrogen has 1 valence electron. So for hydrogen, it's 1 minus how many electrons are circled for this hydrogen? 1. So 1 minus 1 is 0. What about this hydrogen? Same situation. 1 minus 1, 0. Oxygen has 6 valence electrons. How many circled electrons do I have? 1, 2, 3, 4, 5, and 6. So 6 minus 6, also 0. Not very exciting. All the formal charges are 0. Okay, let's look at a different molecule. Let's take a look at this version and one of these 3. We don't need to do all 3 because they're pretty much the same thing. But let's take a look at this and all 3 of these. In fact, let's just do it on the same page. Okay, so imagine a circle around this oxygen that cuts halfway through any bonds that that oxygen is connected to. Oxygen normally has 6 valence electrons, minus how many circled electrons do I have? 2, 4, 6, and 7. So 6 minus 7 is -1. That oxygen has a -1 formal charge. In fact, all 3 of these oxygens are going to have -1 for their formal charges. What about nitrogen? What's the formal charge on the nitrogen in this resonance structure? And I guess I should write out the word resonance for those who can't spell it just from hearing it. Resonance structures. That's what all of these guys are. Anyway, going back to what I was saying. So how many valence electrons does nitrogen normally have? 5. How many electrons are circled? 3. 1, 2, 3. That's what they mean in the formula when they say half the bonding electrons, but I think adding fractions to it just makes it easier for students to forget it or not understand it well. I think I'd rather have students understand what formal charge is than memorize how to calculate it. Because really when you think about it, it kind of makes sense. So Nitrogen, 5 valence electrons. Right now it's surrounded by 3. It's normally surrounded by 2, so it's kind of like it has a charge of positive 2. It's sharing electrons. It didn't actually lose electrons per se, but it's kind of like it lost 2 electrons. It's kind of like it has a positive 2 charge. Whoops, that should be plus 2, not 2 plus. 2 plus would be ionic charge. Okay, so yeah, this nitrogen has a positive 2 formal charge. Okay, let's look at one of these 3 resonance structures. Let's take a look at, first of all, this oxygen is not going to be any different from this one. Same situation, same everything, so it's going to be a -1. That one's also going to be a -1. This nitrogen, normally it has 5 valence electrons. Normally it's surrounded by 5 electrons, but right now its nearest electrons, you've only got 4 that you can count on having nearby at any time. So 5 minus 4, that would be 1. So positive 1 is the formal charge on this nitrogen. And the formal charge on this oxygen is going to be 0, because if you draw a circle around it, you've got 6 electrons caught in that circle. So oxygen normally has 6 valence electrons minus 6 circled electrons gives you a formal charge of 0. And yeah, these other 2 are basically the same as this, except just rotated right or left. Okay, so now we've looked at formal charges, but what do they even mean? How do we use formal charges to determine the quality of a resonance structure? Well, we have a set of guidelines, emphasis on the word guidelines. These rules don't always work, and I believe I forgot to prepare an exception, an example of an exception where these rules don't necessarily work, but just know that exceptions do exist. Anyway, the rules are: a molecular structure in which all formal charges are 0 is preferable to one in which some formal charges are not 0. Number 2, if the Lewis structure must have non-zero formal charges, the arrangement with the smallest non-zero formal charges is preferable. So if you get formal charges of -2 or +2, that's kind of bad. -1s and +1s are better. 0 is the best, but if you have to have charges, try not to let them go past 1s. And if you have to have 2s, then try not to have them go to the 3s, and so on and so forth. Number 3, Lewis structures are preferable when adjacent formal charges are 0 or of the opposite sign. So when 2 atoms are next to each other, their formal charges, it would be best if they're both zeros or both opposite charges. Number 4, when we must choose among several Lewis structures with similar distributions of formal charges, the structure with the negative formal charges on the more electronegative atoms is preferable. So if you have to have positive and negative formal charges, try to get the negatives on things like oxygen and fluorine and maybe nitrogen. Try not to get them on the less electronegative atoms. Try to assign negative formal charges to high electronegativity atoms and positive formal charges to the ones with less electronegativity, if you have the option. And there is another rule which they don't mention here for some reason, but generally speaking, this is rule number 5. structures that obey the octet rule are better than structures that don't. Are usually better than structures that don't. This isn't always true, but it is generally true. I wonder if they have the example somewhere in here in this book I've got in front of me. Let me look for it real quick. I might actually have it. Okay, well, I see one example of an exception to the rules, which I can show you later. But let's take a look at our current example of the nitrate ion. So these three structures are equivalent, so there's no point in comparing them to each other. But I'll compare this structure and this structure to each other. So according to our guidelines, you want to have as many zero formal charges as possible if you have the choice. In this structure, we've got a zero formal charge on one of the oxygens. In this structure, we don't have any zeros at all. Guideline number 2 says we want our non-zero charges to be as small as possible. Here, the biggest formal charge is a 1, whether it's a positive 1 or a negative 1. We're just concerned with magnitude here. Meanwhile, for this structure, we've got a formal charge of positive 2. Not good. Guideline number 3, Lewis structures are preferable when adjacent formal charges are 0 or of the opposite sign. Well, here, the adjacent formal charges are opposite signs. The negative formal charges are right next to the positive. And same here. Negatives are right next to positives, so not much of a contest there. And guideline number 4, we prefer to have the negative charge on the most electronegative atoms possible. Both of them are kind of tied in that case. If you have to have negative formal charges, put them on the atoms that have more electronegativity. Oxygen has higher electronegativity than nitrogen, and in both of these cases, the oxygen gets the negative formal charge while the nitrogen gets stuck with the positive. Okay, and again, rule number 5, which I added, obeying the octet rule is usually preferable. This structure does not obey the octet rule for all of the atoms, while this one does. So this structure, in fact, this family of resonance structures is better than this one on the basis of the octet rule, on the basis of keeping the magnitude of the formal charge as small as possible. There you've got a positive 2, which is bad news. And on the basis of having at least one zero. The more zeros you have, the better, generally speaking. But again, these rules are not set in stone, and you will find lots of exceptions, so don't delude yourself into thinking you can predict which resonance structures are really the best. It's not as clear-cut as those guidelines might make it out to be. So let me show a bit of an exception. I guess it's not really an exception when you count my 5th guideline, but the phosphate ion. So they've got 2 different structures for it. They've got 2 different structures for the phosphate ion, and I'm not going to walk through the steps this time. I'm just going to write it out. or draw it out. So here's one resonance structure for the phosphate ion. Whoops. There's one resonance structure for the phosphate ion, and here's another one. By the way, when we write multiple resonance structures for the same molecule or polyatomic ion, we use double-headed arrows like this. Don't confuse them with these double hooks, which we will see later. Those are for equilibrium equations, not for resonance structures. Resonance structures, we show that they're different structures of the same molecule or ion through double-headed arrows, not double hooks. Okay, P, and then we've got an oxygen there, and I think that's right. Yeah, that's what they've got in the book. Close the bracket, and -3. Oh, and by the way, something else I forgot to mention about formal charges. When you add up the formal charges of all the atoms in a structure, they should add up to the total charge of the ion or molecule in question. So if I do -1 for this, plus -1 for this, plus -1 for this, for all three oxygens, plus +2 for nitrogen, in total that's -1, which is the total charge of the nitrate. Same thing over here, so 0 plus 1 is 1, minus 1 is 0, minus another 1 is -1. So the total of the formal charges should be the total charge of the ion or molecule. Anyway, they gave us the formal charges for these oxygens and the phosphorus. So over here, they gave us +1, -1, -1, -1, -1. And here they gave us 0, 0, -1, -1, -1. Either way, those add up to -3. We've got -1, 2, 3, 4, plus 1 is -3. And here we've got 0 and 0 and 3 -1s. That's another -3. Anyway, which of the two structures would be correct based on the 4 guidelines that were presented by the book where I got these from? Well, according to these rules, because they don't take into account the octet rule, you would think that the structure on the right is the better structure because it's got more zeros in it. You would think this one's better because it's got more zeros in it versus this one. But in fact, it turns out that this is the better structure. This is the better structure, and we know that from let's see, do we know that from experimentation or was it theoretical calculations? No, based on theoretical calculations. Based on complicated calculations. Calculations that are beyond the scope of this course. You're not going to be expected to know how to do them. I don't think I know how to do them, but I think I know enough physics where I could learn if I ever wanted to. So yeah, that is what inspires me to also add the 5th guideline, which is try not to violate the octet rule. The problem with this one is that the phosphorus has more than an octet, which is fine. You can have more than an octet, but you don't have to. You can have just an octet, and usually having just an octet is better, but I've also seen exceptions to that, so Like I said many times throughout this video, a lot of these rules, so to speak, are not rules, they're just guidelines. They're just trends. They're general patterns that don't work for every single case. If you want hard rules, study physics. In chemistry, there's only guidelines and trends with lots and lots of exceptions. Okay, so that's formal charge and resonance structures. Now it's time to talk about the strength of covalent bonds. Now it's time to talk about the strength of covalent bonds. Let's go ahead and add a new sheet. Strength of covalent bonds. How are we doing on time? Okay, better than I expected. Maybe this video won't be as long as I expected it to be. Then again, maybe I'll just eat up the time doing practice problems. Anyway, strength of covalent bonds, or maybe I should say strengths of covalent bonds, plural. So, strengths of covalent bonds. First thing I want to look at, or first thing I want to show you, is this chart that compares the length of a bond to the strength of a bond. Okay, so if we take a look at each of the bonds represented, you've got the single bond between carbon and carbon in the first row, then a double bond between carbon and carbon in the second row, and then a triple bond in the third row. So same two atoms, but different numbers of bonds between them. The more bonds you have, the shorter the bond length. If you look in the second column, the single bond for carbon gives you a bond length of 1.54 angstroms. If you've forgotten what an angstrom is from the previous video, 1 angstrom is 1/10 of a nanometer. It's 10 to the negative 10 meters. But yeah, 1.54 angstroms is the length of the single bond. The double bond is shorter, it's 1.34, and the triple bond is even shorter, it's 1.20. The more tightly bound together they are, the shorter the bond, the closer they are to each other. And I guess you could think of this as being similar to what happens when you put a bunch of rubber bands around an object that is big enough where you'd have to stretch the rubber bands. I don't know if you've ever seen that. I think it was a Slow-Mo Guys video on YouTube where they kept on putting more and more rubber bands on a watermelon, and the watermelon kept on getting more and more squished until at one point it exploded, and they captured it on camera with a high-speed camera and played it in slow motion. I think it was the Slow-Mo Guys, but if I find the video, maybe I'll link to it. Or maybe you can find it yourself. Whichever is faster. Anyway, that's carbon-carbon. If you look at carbon-nitrogen, same thing. Single bond is longer than the double bond, which is longer than the triple bond. So the stronger the bond, the shorter the length. That's the general trend. Carbon-oxygen, same trend, 1.43, then 1.23, then 1.13 for those last three rows. And of course, you also see the bond energies over there. We'll talk about that in a bit. So, yeah, the strength of covalent bonds is going to have a direct effect on their length. If you've got similar covalent bonds between the same pairs of atoms, then the higher the bond order, that is if it's a single, double, or triple, The higher the bond order, the shorter the bond length. Another factor that affects the strength of a covalent bond is bond polarity. The more polar a bond generally, again, this is not a strict rule, but more bond polarity usually means stronger bond. Usually means stronger bond. And bond polarity actually depends on two things. One thing you already know, which is the difference in electronegativity, but the other thing is the distance between the partial charges. When you combine those two factors, you can calculate what's known as the dipole moment. That's more of a concern for physics people, but I think it's a simple enough concept that it'll be worth talking about when we get into the intermolecular forces. But yeah, generally speaking, the greater the difference in electronegativity, the stronger the polarity, and therefore the stronger the bond. But you do also have to take size into account, which messes with things. So if I were to compare, let me see, let me go back to my electronegativities table and see what two bonds I could compare. If I were to compare the hydrogen-nitrogen versus hydrogen-chlorine bonds. If I were to compare those, if I were to compare hydrogen-nitrogen versus hydrogen-chlorine. So nitrogen and chlorine are said to have the same electronegativity, according to the table, and hydrogen is going to have the same electronegativity as another hydrogen. So same electronegativity differences between these two, but one of these bonds is more polar than the other, and it would be this one. This one would be more polar, because polarity isn't just about how much charge is separated, which depends on the difference in strength, or difference in electronegativity rather, but it also depends on how far you can separate the positive charge from the negative charge across this bond. And since chlorine is bigger than nitrogen, it's one row below nitrogen. It's got one shell more than nitrogen. It will be able to pull the electrons a greater distance and therefore create a more polar bond. So I would expect the bond between hydrogen and chlorine to be stronger. In fact, the bond between hydrogen and chlorine is probably an ionic bond, right? HCl, hydrochloric acid, is, well, an acid, and acids fall under the category of ionic compounds. Though, really, I should say that hydrochloric acid is a mostly ionic compound, because it does also have some properties of covalent compounds. In fact, the idea of bond strength being related to differences in electronegativity between atoms kind of makes it so that there is no pure covalent bond and there is no pure ionic bond. It's just that some bonds are very ionic and some are very covalent and some are in between. So it all lies on a spectrum. It all lies on a spectrum. But maybe now I'm making your brains hurt more than I should. Anyway, generally speaking, more bond polarity means a stronger bond. For now, just focus on the electronegativity part of it. Don't worry about the length part of it. That was just extra FYI stuff. Okay, and finally, you noticed this in the chart I pulled up. There was a, what was it called? What did they call it? Bond energy? I think that's what they called it. Yeah, they called it bond energy. It goes by different names. Some people call it bond enthalpy. Some people call it bond dissociation energy. So there's one table of a bunch of bond dissociation energies or bond enthalpies. And there's more to this. Let me pull up another table. Ah, yes. Put that up on top of it. So yeah, there's a lot of different enthalpies associated with a bunch of different bonds, and bond energies are defined as, bond dissociation energies are defined as the amount of energy required to break a bond. So bond dissociation energy, and it looks like this marker is close to dead. Bond dissociation energy. Bond dissociation energy is the energy required, to break a bond. Energy required to break a bond. And you'll notice in the table that I just had up that all of the bond dissociation energies were positive. There is no such thing as a bond that you break that releases energy or gives you energy for breaking it. You have to put energy in to break the bond. Energy required to break. Yeah, I guess that's not grammatically correct, but energy required to break a bond. There. Okay, so with bond dissociation energy, it kind of, because of the way it's defined, it doesn't work quite the same way as heats of formation from back when we did thermochemistry. I think that was like 2-3 videos ago. So bond dissociation energy does not quite work like heats of formation. Heats of formation are the energies associated with forming a compound, but bond dissociation energy is the opposite. It's the energy associated with unforming a compound, breaking a bond, rather than making something. So, for bond dissociation energy, rather than doing energies of products minus energies of reactants like we did with heat of formation, we do the opposite. We do energy of reactants minus energy of products. This is for bond enthalpies specifically. For bond enthalpy or bond dissociation energy, for bond enthalpy, delta H for a reaction is equal to, let's see, it's equal to, I guess I'll call it D for dissociation, D of reactants minus the bond dissociation energies of products. You could reason that the amount of energy required to break a bond is the exact opposite of the amount of energy that you get when you make a bond. If breaking a bond requires energy, then making a bond releases energy. And we assume, quite reasonably, that the energy gained by making a bond equals the energy required to break that bond in the first place. Okay, so let me give you this example that I've prepared for working with bond enthalpies. Which one should I start with? I think I'll leave the two on the top for later. Let's do the one on the bottom first. So for the one on the bottom, first off, you want to draw the Lewis structures to figure out what you're looking at. So 2NCl3, I think I'll do that. Where should I do it? Oh, I've got this piece of paper that I didn't finish using for some reason. So yeah, let's do it here. We've got 2NCl3, so that's going to be nitrogen is the central atom, 3 chlorines. I'm just going to do it quick rather than walk you through it. But you're free to pause or slow down the video if you want to check my work. Never trust my work. I make mistakes too. So we've got 2 of those. I'm just going to draw 2 of them. Normally I would just put a big 2 in front of there, but this time I'm going to draw it all out. Okay, so we've got 2 of those, and they react, their bonds break, and we form N2, so that's nitrogen. It's going to look like this. Nitrogen gas is going to look like that, plus 3 chlorine gas. Chlorine gas is going to look like this. And we've got 3 of those. Later on, you'll see me draw Lewis structures where I don't bother drawing the lone pairs just to save time. So be prepared for that. Get used to looking at Lewis structures that don't show the lone pairs and just kind of imagining, calculating how many lone pairs would actually be there. With practice, you can get better at it. Anyway, so bonds broken, bonds made. Let's figure out what the energies are associated with these. First of all, how many bonds am I breaking and of what type? I have 3 bonds and all of them are nitrogen-chlorine single bonds. So I've got 3 NCl singles. So that's the dissociation energies of reactants minus the dissociation energies of products. So dissociation energies of reactants, let me put that in all in one big bracket. And dissociation energies of products I should subtract since I'm making those bonds rather than breaking them. So we've got a nitrogen-nitrogen triple plus 3 chlorine-chlorine singles. Okay, let's figure out what those values are from our charts. Do I have chlorine-chlorine single? I see it right there towards the right, a little bit towards the middle. It's 243. So I'm going to write that down, 243. Do I have my nitrogen-nitrogen triple? I don't see it in that first chart. It might be in the other one. So before I flip to that other one, do I have the nitrogen chlorine single? Yes, I do. It's towards the top of the second column. NCl is 200. So there's that. And let's see if I can find my nitrogen triple. Ah, there it is. Towards the bottom in the middle, 946. By the way, in case you needed more confirmation that triple bonds are stronger than double bonds, which are stronger than single bonds, you might want to notice that just looking at the nitrogen single, double, and triple, you see the bond energies go up as the bond order goes up. Triple bond has the highest bond enthalpy, single bond has the lowest among the nitrogen bonds. I feel like I may have pointed out something similar earlier in the video, but just in case I forgot, there it is. I'm gonna need to make a note to myself for, I think, the next video to go back and revisit this and do some math. But anyway, back to our problem at hand. So we've got 3 times 200. Actually going to use the calculator. 3 times 200 minus 946, and also minus 3 times 243. And that gives us a grand total of negative 1075. So heat of reaction for this process is going to be negative 1075 kilojoules per mole. Since delta H is negative, that tells me that this process is exothermic. The energy released due to bonds being made was greater than the energy required to break the bonds that were present in the beginning. All right. Now for the other two, so let's check this off our list. For the other two, I'd like to point out something that a lot of students tend not to notice, especially when they're first experiencing these types of problems, which is that any bonds that show up on both sides of the equation, you can assume they were never broken or formed to begin with. You might as well. You can think of them as being unaltered. So for a question like this one, I'm not going to put the table out in front of you. I guess you can rewind part of the video and cheat, but I'm going to give you very limited information here and see if you can figure out what to do. For this one, I can tell you that the CN triple bond has an enthalpy of, where did it go? 891 kilojoules per mole. And I can also, wait, actually no, you don't need to know that information. Never mind. I messed up. Gave you the wrong info. You do not need that. What do you need? Carbon-carbon double and carbon-carbon single. So 611 and 345. Carbon-carbon double is 611, and carbon-carbon single is 345 kilojoules per mole. Okay, so some students will be presented with a problem like this. This is the only information given to them. They're not given access to a table of values, and they look at this and they think they can't do it, that the problem is unsolvable, and they just quit because they feel like something's wrong. That's not true. Truth is that this is all the information you need. You do not need to know the energy of the CH single bond, and you don't need to know the energy of the CN triple bond. Why? Well, let's look at the math. So how many CH single bonds do I have on the left? I've got 1, 2, 3, 4, 5. I've got 5 CH singles plus a CC double and a CN triple. Okay, so that's the reactant side. Let's put that in brackets. Minus dissociation energy of products. What do I have on the product side? I've got 5 CH singles. 1, 2, 3, 4, 5. 5 CH singles. I've got a pair of CC singles, one here and one here. So that's 2 CC singles plus a CN triple. Well, would you look at that? We've got the 5 CH singles minus 5 CH singles cancels out, and a CN triple minus a CN triple cancels out. So all we're left with is a CC double minus a pair of CC singles. So 611 minus 2 times 345. That's 611 minus 2 times 345 is negative 79. Delta H reaction is negative 79 kilojoules per mole. Kilojoules per mole. That's some really bad handwriting. Let me try that again. Negative 79. Okay, that's more readable. But yeah, there you go. You don't need as much information as you think you do. Essentially, you could have started this problem by canceling any bonds that show up on both sides. Let's take that approach with this next one just to see how that goes. So I see carbon-bromine single bonds on both sides. I'll cancel one here with one here, and that one with that one, and that one with that one. CH single bond doesn't cancel with anything there, and CL-CL single bond doesn't cancel with anything there. I've done all the cancellations I can, so all that's left is a CH single plus a CL-CL single, and then all that minus a CCl single. Whoops, did not mean to. Brackets, parentheses, CCl single plus a single, or one HCl single, plus parentheses, HCl single, close brackets. Okay, so I just need to look up 4, well actually 3, because I still have, oh, no I don't. No I don't. I need to look up 4 different values, so let's see what we've got. Carbon, hydrogen is 415. Chlorine, chlorine is 243. I think we used that earlier. Oh yeah, we used it back there. Carbon chlorine is where is carbon chlorine? Do they even have it here? Maybe it was on the other table. Carbon chlorine. There it is, 330. And hydrogen chlorine is 432. Okay, so 415 plus 243 minus 330 and also minus 432 is negative 104. All of these reactions have been exothermic. Negative 104 kilojoules per mole. Okay, there we go. So there's strength of covalent bonds and energy of covalent bonds. Now, I guess all that's left is to look at some example problems for, I guess we didn't really do any example problems for periodic properties. Oh, right, and we also need to talk about photoelectron spectroscopy. Should I do periodic properties problems first? Yeah, I think I'll do that first, and then we'll save photoelectron spectroscopy for the end. Okay, periodic properties, let's start there. And close that down. Let me see. I think I'm just going to kind of talk through some of these because they're more conceptual. If I feel that I've covered the topic thoroughly enough that you'd know how to do it, then I'm just going to skip the problem and move on ahead. 67, based on their positions in the periodic table, predict which has the smallest atomic radius. Okay, yeah. You should be able to do that on your own. Again, as you go up and to the right, atomic radius decreases. And the decrease from up to down is more important than the decrease from right to left. So I guess something I didn't really talk about was if you have two different elements that are at corners from each other. Let me move this out of the way and put this in its place. I don't know if you can tell from the video, but when I tried to prepare this sheet earlier, I had a little bit of a mishap, so I kind of folded the side, and yeah, didn't want to write on top of that because I had a feeling the edge where I folded the paper would have messed with my writing. Anyway, if I were to compare, let me see. If I were to compare, let's do potassium, calcium, and magnesium. Let's see, potassium, calcium, and magnesium. Is that right? Is that the right example that I'm trying to illustrate? Maybe I've been recording for too long and I'm starting to lose it. Let me think for a second here. What am I trying to show? So if I look at my periodic table, oh, no, not potassium, sodium. Okay, there we go. So if I was told to arrange these from biggest to smallest, I think this just kind of goes without saying, but just to be on the safe side, we know that We know that sodium is bigger than magnesium because it's to the left of magnesium. We know that calcium is bigger than magnesium because it's below magnesium. So which one comes first? It's definitely the calcium. Sodium is further to the left, and calcium is not as far left as sodium is, but that doesn't matter because calcium being one row below is more significant than sodium being one column to the left of calcium. So calcium is still bigger than sodium, and then of course magnesium would be the smallest of the three. So that's just something I wanted to point out. Probably should have pointed it out as an example way back in the beginning. But yeah, there's that. So 67, 68, I would expect you to be able to figure out on your own. 69, same thing, but for first ionization energies, you should be able to do that just fine on your own. 70, smallest first ionization energy, so basically the same as 69. First ionization energies again, 72, more ionization. 73. Atoms of which group in the periodic table have a valence shell electron configuration of ns2np3? Okay, so that's more of a question for the previous video, but if you had, for example, a 2s2 2p3, or a 3s2 3p3, or a 4s2 4p3, or anything like that. Any atom whose valence shell configuration follows that format would have how many valence electrons? 5. 2 in the s orbital of the valence shell, and 3 in the p orbital. And the atoms that have 5 valence electrons are all in the same column. Nitrogen, phosphorus, arsenic, antimony, bismuth, and I forget what they named the new element. I'm looking at an old periodic table. Let me see what 74 says. Okay, so 74, that refers to the second column of the periodic table. That's where all the S2s are. So yeah, this stuff is from is related to material we covered last time in the previous video. 75, order of increasing radius, we've done that. Visuals, or not visuals, what am I looking at? Problems for periodic properties and trends. Let's look at this next set. 76. Increasing radius, we know how to do that. Ionic radius, we know how to do. Which atoms and or ions are isoelectronic with bromine plus? Okay, well, I already explained what isoelectronic means, so you should be able to handle that on your own. 80 is more of the same. Hmm, 81 is simple enough. 82, of the 5 elements, which has the most exothermic reaction? E represents an atom. What name is given to the energy for the reaction? Note the process depicted does not correspond to electron affinity. Why does it not correspond to electron affinity? Okay, I'm not sure about their hint for 82, but you should be able to figure it out just based on the trend for electron affinity. Number 83 of the 5 elements, which... Oh, I see what they mean for number 82. I see what they mean. Okay, that's a bit of a trick question. I see what they mean by the hint. So, if you write that equation backwards, what's that energy going to be? Let's actually do this one. Let's write it out. It's worth it. So if I write that equation backwards, then I have unknown substance E becomes unknown substance E with a positive 1 charge plus an electron. What's this? This is the first ionization energy of substance E. First ionization energy of substance E. So when they ask for which of the 5 elements is the reverse of this, most exothermic, well, it's the one for which this is most endothermic. So the more energy it takes to achieve this, the more positive delta H associated with this process, the more negative delta H associated with the original process. So delta H of that orange process is the negative of the delta H of this magenta process. So they're asking for the magenta process. For which element would it be most exothermic? And it would be the one for which this is the most endothermic. Now, ionization energy being most endothermic means ionization energy being highest, the energy required being highest, which would require the most energy to ionize. And I think that's as far as I'm going to walk you through it. I think you can figure out the rest on your own. All right. 83, kind of the same idea. '84, the ionic radii are given. Explain why these ions have different sizes even though they contain the same number of electrons. Focus on the protons. We've been through this. 85. Which main group atom would be expected to have the lowest second ionization energy? Those would be the atoms of group 2 specifically, and it would have to be then the biggest atom of group 2. Lowest second ionization energy. So highest second ionization energies would definitely be group 1. Because with group 1, first column of the periodic table, if you remove the first electron, the next electron you remove is 1 shell deeper. We talked about this when discussing successive ionization energies. Whichever electron you remove after the first is going to cost more, but it's going to cost significantly more if it's in a deeper shell. So first column, definitely not in the running. That leaves you with the next best option, which is the second column of the periodic table. Their first ionization energies are going to be higher than the first ionization energies of the first column, but their second ionization energies will be lower than the second ionization energies of the first column. So yeah, it would be group 2 elements. You probably were able to figure that out on your own. But for the people that didn't make that mental leap, there you go. 85. Wait. No, we just did 85. 86. Explain why aluminum is a member of group 13 rather than group 3. Okay, so that's a question about the numbering of the groups of the periodic table. So I think that's stuff that you can just read about in your book, but basically there's two different ways that the periodic table, the periodic table's groups are numbered. Let me actually switch to my periodic table visual. We haven't seen this in a long time. So if you look at the tops of all the columns, then you see two different numberings. Actually, I guess you see three different numberings. One of them is in Roman numerals. But ignoring the one that's in Roman numerals. So first column is numbered 1. It's also numbered 1A. Second column is numbered 2, also 2A. And then if you look to the 13th column, it's numbered 13, but it's also numbered 3A. So the A numbering is basically the one that excludes the yellow block and the green blocks in the bottom. It's the one that skips the transition metals. It's the main groups. So aluminum is in the third main group, but the 13th group overall. So yeah, that's what that's all about. You can read more about it in your book probably, or online, since most people can't be bothered to read their books. And that was 86. Okay. Let me see. I had problems involving electronegativity and polarity. Do I want to look at any of those? Let's see. From its position in the periodic table, determine which atom in each pair is more electronegative. Yeah, that's just, again, a comparison you can make based on the fact that electronegativity increases as you go up and to the right along the periodic table. Going up is more significant than going right. So that's how you would handle 16. Don't cheat and read the values off of that one visual I showed you earlier. You really should be able to just do it qualitatively. 17, from their positions in the periodic table, arrange the atoms in each of the following series in order of increasing electronegativity. Okay, so more of the same. So let's look at the next one, or the next set. Identify which bond is more polar. So basically you want to look at electronegativity differences between the atoms in each pair. And it looks like they made it so that you don't have to read the electronegativity values. Because, for example, with part A, it's HF or HCl. We know that in both cases it's something with H. So really it's just a comparison between fluorine and chlorine. Part B is really just a comparison between nitrogen and carbon, and so on and so forth. Yeah, it looks like all of these have one atom in common for each pair. So you shouldn't need the chart that has all the electronegativity values for number 21. 22, which of the following molecules or ions contain polar bonds? So First of all, you can cross out anything that's just one type of atom because, for example, part A and part B and part C, if you have a bunch of oxygens together, they have equal electronegativities to each other, so there's no difference in electronegativity, so there couldn't possibly be enough difference to create a polar bond. Same reasoning applies to sulfurs with other sulfurs. D, you might want to consider the electronegativity difference between nitrogen and oxygen. E, you might want to look at the difference between carbon and oxygen. F, you want to look at hydrogen versus sulfur. And G, you want to look at boron versus hydrogen. And use that guideline I showed you. Less than 0.4 is probably nonpolar. Between 0.4 and 1.8 is probably polar. And anything past 1.8 is probably ionic. But that's it for 22. Let me see. Any problems here for... Well, we already did Lewis structure problems, but in case you wanted more practice, you've got these to look at. And I guess here's even more practice for that. And also it looks like they asked for formal charge, so if you want practice determining formal charges, there's that, but we've already done examples of all of this. This next set, it looks like they've got comparing resonance structures. We did an example of that. Actually, I think we did 2 examples. No, we did an example and an exception. But yeah, using formal charges to compare resonance structures and determine which ones are more representative of the actual molecule. We've done that. So I'm skipping it, but there it is in case you wanted to practice. What do these others say? Yeah, all of these are formal charge practice, so I would definitely recommend looking at a bunch of them. But it's nothing different from what we've already done. This over here, so just taking advantage of what we mentioned earlier about bond strength. Generally speaking, the stronger a bond is, the greater its bond dissociation energy. So that should be like our ultimate meter stick of which bonds are stronger. But yeah, look at bond order. So double bonds are better than single bonds. Triple bonds are better than double bonds. Compare bond polarities if you have to, on the basis of electronegativity differences and what was the thing I mentioned earlier? On the basis of atomic size as well, because bigger atoms will have to make longer bonds. So compare on the basis of those when you can't compare on the basis of bond order. So yeah, take size and polarity into account when bond order... Did I say size and electronegativity difference? Take those into account when You can't just answer it on the basis of bond order. And if all else fails, you can just pull up the charts that have all of the bond dissociation energies and check your results. Okay, I think that's it for those problems. We didn't really need to go over most of them because we've already covered examples of them. Let's take a look at photoelectron spectroscopy. Let's take a look at photoelectron spectroscopy. So, what is photoelectron spectroscopy all about? This is something that I had never encountered until I think maybe 2015, 2016, when I tutored an AP chemistry student who showed me one of those Princeton Review workbooks, and it was the first time I had ever seen anything of that sort. But I learned later on that it was added to the AP curriculum. So photoelectron spectroscopy, or PES for short. Photoelectron spectroscopy, or PES for short. Basically, the idea behind it is that you fire beams of energy at atoms, and those atoms will then eject electrons. You can calculate the energy of those ejected electrons, and based on that you can figure out how much mechanical energy they must have had while they were in the atom. And from that you can actually determine the electronic structure of the atom. You can figure out what the electron configuration is. Photoelectron spectroscopy is why we know about that exception that I mentioned in the previous video for the electron configurations of chromium and molybdenum and copper and silver, for example. If you don't remember what that was about, I suggest going back to the previous video. But yeah, so let me show you what the setup is, what the apparatus looks like for photoelectron spectroscopy. There it is. So you just send some beams of light, high energy beams, typically X-rays, sometimes ultraviolet rays. But you fire some high energy rays at a sample, and then your sample will eject electrons. Those electrons are collected by a detector, and the detector kind of measures how many electrons hit it and what kinds of energies those electrons have. And you're firing these beams of X-rays on multiple atoms. So electrons are being ejected out of multiple atoms at the same time. It's not like you're trying to eject all the electrons of a single atom out at once. And remembering that is important if you want to understand why we can get these nice looking graphs that you're going to see in a couple minutes. Actually, there's an example of a graph right there in the bottom right corner of the drawing, or a diagram. But yeah, so photoelectron spectroscopy, it produces these curves, and basically the skill you want to learn here is how to read those graphs, those spectrograms as they're called. Okay, so let me show you an example of such a spectrogram. Basically, you might get something that looks like this. And actually, let me remove the apparatus from the background so it's easier to read. Yeah, there we go. So What you see there is a bunch of different peaks, a bunch of different signals that were detected, and this is actually a rather clean looking graph. If you do this in real life, it's going to look a bit uglier. In fact, let me show you that real quick. This is what it looks like in real life. Not as easy to read, but you could figure it out if you had to. Anyway, back to the nicer looking spectrogram. So depending on who's providing the graph, some people will label the horizontal axis as ionization energy. Some people will label it as binding energy. They're practically the same thing, so I wouldn't worry about it too much. All you need to remember is the electrons that are associated with higher energies are the ones that are closer to the nucleus. They're the ones that are harder to remove. That concept shouldn't be foreign to you since we talked about ionization energy earlier in this video. And then on the vertical axis, you've just got the relative number of electrons. You don't actually get the absolute number of electrons, but if you know your stuff, you can figure out what the heights of the peaks correspond to. If I look at the far left and start looking at the numbers from left to right, I notice something unusual, which is that the axis is numbered in descending order from left to right. Some of these graphs will be in descending order, some of them will be in ascending order. It depends on who's providing the graph. Everybody has their own way of doing it. But that's the first thing you want to check. Figure out where the highest energy peak is and where the lowest energy peak is. So in this example, highest energy is to the left, and lowest is to the right. It's nearly zero. Okay, the highest energy peak at around 347, it looks like, or I guess that label up above says it's 349. 349 megajoules per mole. That would correspond to the closest electrons to the nucleus in that atom. Those would be the 1s2 electrons, so that peak represents 2 electrons. Then as you go to the right, there's a little bit of a wavy break thing that you see in the axis. That's just to signify that they're skipping a bunch of numbers, because otherwise you'd have a very long and mostly empty graph. So that's what that wavy thing in between the 345 and the 37 is about. It's just them showing that they've skipped a big chunk of empty graph space to make the picture fit in a smaller space. But yeah, so that next peak is the next highest in energy to remove those electrons. So that would tell me that that 37.1 megajoule per mole peak corresponds to the 2s2 electrons. Then the next peak appears to be 3 times as high as those first 2 peaks. If those first 2 peaks represent 2 electrons each, then that third peak, which is 3 times as high, probably represents 6 electrons. I would suspect that's a 2p6. And once you understand this, you can basically read it like an electron configuration. From left to right, it's 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. That last little peak is 4s1 because it's half as tall as the s2 peaks that we already accounted for. So based on that, we can actually tell what atom this was. This was, let's see, potassium. This would have been potassium. It ends in 4s1, that's potassium. Okay, so that's a basic photoelectron spectrum, but of course there's a lot more to unpack here. So I think the best way to learn about this stuff is to just kind of look at some example problems. Let's go ahead and look at this one. So this, I believe, I grabbed from Khan Academy. They want us to identify an element based on its photoelectron spectrum. Notice that this time they have the axis going up as you go to the right. So the highest energy peak is the furthest to the right, and the lowest energy peak is furthest to the left this time. And that means we basically have to read it backwards. So it looks like, and they were kind enough to give us the numbers of electrons that each peak corresponds to. Those are the numbers 1, 2, 6, 2, and 2 for the one in the top row. But yeah, we want to read this backwards. So start from that top row and go right to left rather than left to right. So that top peak at 151, hardest electrons to remove, those were the 1s2s. Then next one is at 12.1, that's the 2s2. Then at 7.19, that's the 2p6. At 1.09, that must be 3s2. And then at 0.58, that must be 3p1. Which element do I have that has an electron configuration that ends in 3p1, assuming everything else followed the Aufbau principle? That would be aluminum. That would be aluminum. Okay, so we've identified that element. Let's see. Does this next problem give us anything else that we need to call attention to? So it's asking which element the spectrum is for. We've already done 2 examples of that so far. And I think that one's also aluminum. Yeah, it is aluminum. And then they want us to write the electron configuration. You know how to do that. Let's take a look at the next one. Identify if either of the following statements is correct. If yes, why? If not, why not? So part A says the photoelectron spectrum of magnesium ion is expected to be identical to the photoelectron spectrum of neon. That is wrong. So what you would expect to see, you've got equal numbers of electrons, but you have unequal numbers of protons. And more protons means it's harder to remove the electrons from the magnesium ion than it is from the neon ion. So if you were to draw 2 spectrograms, one for neon and one for the magnesium ion, they would look kind of identical, except that for the magnesium, all of the peaks would be at higher energy, or at least the ones that are highest in energy would be higher in magnesium ion than they are for ordinary neon. And I think we'll see an example of that later that illustrates it visually. Part B, the photoelectron spectrum of chlorine-35 is identical to the photoelectron spectrum of chlorine-37. Yes, because chlorine-35 and chlorine-37 are isotopes. They have different number of neutrons, but in terms of electrons and protons, they are the same. Neutrons are not going to have any notable effect on your photoelectron spectrum. Okay, here it is. Here's the illustration I was talking about just now. So if you look at these 3 spectrograms, one of them is for nitrogen, one is for oxygen, and one is for fluorine. And what you'll notice about them is that, yeah, the total number of electrons represented is different. That goes without saying. But the other thing that you notice is look at the highest energy peak for each one. For nitrogen, the highest energy peak is at 39.6. For oxygen, it's at 52.6, and for fluorine, it's at 67.2. That's because fluorine has the most protons. The more protons you have, the more energy it'll take to remove the 1s2 electrons. So you would expect to see something similar going on if you compared the spectrograms of magnesium ion and ordinary neon. More protons means higher energy for the 1s2 peak, and you'd expect to see higher energies for several other peaks until electron shielding effects start messing things up. But yeah, that's all I wanted to point out with those three. And now we've got a bunch of sample questions. I guess I'll go through the ones that go over an idea that hasn't been mentioned yet. Otherwise, I'll skip over what we already know how to do. And notice in this spectrogram, they have it from highest energy to lowest energy as you go left to right. Again, very, very important to start by figuring out where the highest energy is, if it's on the left or the right. I couldn't tell you the number of times I screwed that up and confused myself because I forgot to locate where the highest energy was placed. Anyway, that's a photoelectron spectrum of neon. It says peaks A, B, and C represent the binding energies of electrons in which subshells of neon. We already covered how to do that. 2. Which of the following statements best accounts for peak A being far to the left of peaks B and C? Okay, this is something we haven't talked about, but I think you can figure it out. Peak A is 1s2, peak B is 2s2, and C is 2p6. 2s2 and 2p6 are close in energy because they're in the same shell, while peak A is much farther away because it's inside of an entirely different shell. So let's see, out of those answer choices, I guess I would go with choice C. I would go with choice C. Okay, so that's that one. Let's take a look at this third question, which relates to the same graph. Which of the following statements best accounts for peak C being 3 times the height of peak B because it represents 3 times the electrons? That we've already talked about. Okay, let's take a look at the next one. Nitrogen shows 3 peaks in its photoelectron spectrum. These 3 peaks correspond to the binding energies of 1s, 2s, and 2p electrons. What are their relative heights? So it should be just the ratios of the electrons represented. 1s2, 2s2, 2p3 is the electron configuration for nitrogen. So I should expect peaks with a height of 2, 2, 3. So that's choice B. Number 5, if the binding energy of an electron is between 0 and 10 electron volts, so pretty small, it can be assumed that the electron originated in an s orbital, a p orbital, a core orbital, or a valence orbital. So electrons with low ionization energies, or low binding energies, are electrons that are easy to remove. The easiest electrons to remove are The ones that are furthest from the nucleus, the valence electrons. So in fact, if we go back to the graph of the previous set of problems, you can see peaks B and C are really close to zero binding energy. They're close, but not quite there. So they have a low binding energy. It doesn't take much energy to remove those particular electrons. Okay, so that was question 5. Let's take a look at this. So now we're comparing nitrogen and fluorine. Given the data in the two spectra, what do you expect the binding energy of the 1s electrons in oxygen to be? Okay, so the 1s electrons correspond to peak A in each of those two graphs because they're closest to the left, and to the left is where they put the higher binding energies for these graphs. So let's see, nitrogen and fluorine. Nitrogen has 7 protons in its nucleus. Fluorine has 9. Oxygen is between nitrogen and fluorine. So I would expect the binding energy for the 1s2 peak in oxygen to be somewhere between what it is for nitrogen and fluorine. So for nitrogen, it looks like it's just above 400, and for fluorine, it looks like it's right at 700. So somewhere between 400 and 700 electron volts is where I would expect my peak A to be for oxygen. So that's choice C. Next up, we have number 7. You see that big zigzag through the graph? Again, that's like the wavy thing we saw in the other graph. It's just to signify that they've cut out a big empty section of the graph to fit it all into one page. The photoelectron spectrum shows the binding energies for some element Z. What is the identity of element Z? So you can figure that out. Just read the electron configuration from highest energy to lowest binding energy. So I guess from left to right, 1s2, 2s2, 2p6, 3s2, that's magnesium. Okay, problem sets 8 through 11. Let's see. Here we've got identify the peak in the spectrum of sodium that represents the binding energy of electrons in the 2s orbital. You should be able to do that based off of the examples we've covered so far. Number 9, identify the peak that represents sodium's valence electrons. We also talked about that. Valence electrons would have the lowest binding energy or lowest ionization energy. Number 10, which peak of sodium shows electrons closest to the nucleus? Highest binding energy. We talked about that already. 11, which one represents an orbital containing 6 electrons? So an orbital cannot contain more than 2 electrons. What they really should have said is a subshell containing 6 electrons. The p subshell has 3 orbitals. Each orbital can hold 2 electrons. I know I'm being nitpicky, but you'll thank me later when you encounter a problem based on that minor nitpick in your exam. or maybe you'll get lucky and you won't find such a problem in your exam. Okay, other than that, I think you know how to figure that one out. Let's take a look at the last couple problems for this, and then we can call it a night or a day, depending on when you're watching this. We've got some unknown element Q, and they've got 5 peaks for us. The electrons that feel the strongest effective nuclear charge are given by which peak? We already discussed it. The ones that are highest in binding energy or ionization energy. The ones that are closest to the nucleus would require the most energy in order to free them from the atom. 13. Which peaks represent valence electrons? I would say peaks D and E. Those seem to be grouped in the same shell because peak A is 1, 1s2. Peaks B and C are in shell number 2. They're 2s2 and 2p6. And then peaks D and E would be 3s2 and 3p2. So both of them are in the third shell, which seems to be the highest shell according to this graph. Okay, so that's that. And then one more part to this, or 2 more rather. 14 and 15. Which peaks in the spectrum are given by the binding energy of p orbital electrons? Okay, I think you guys can figure that out on your own, especially because I kind of spoiled it while explaining my answer to the previous problem. 15, what is the identity of element Q? You can also figure that one out just by determining the electron configuration. So yeah, I think with that we are done with photoelectron spectroscopy. Let me think. I guess just a couple of conceptual questions that the really curious students might have. The rest of you probably can click off this video now, but for those who are curious, there are a couple of common questions that students will ask. So first, the idea of successive ionization energies and how the ionization energies get higher and higher as you remove more electrons. How does that not affect these photoelectron spectra? Because when you think about it, let's say I number this from 1,000 to 0. If you think about it, when I have a peak that wait, what am I doing? No, this isn't right. Let me try that again. Okay, and let's put 0 over there. And let's draw an S peak there. And an S peak there. And let's make this a P6. Let's say this is neon. Let's say this is neon. Okay, so some people might be asking, well, if you're detecting ionization energies, then shouldn't you actually be getting a separate peak for each electron? Because, you know, wouldn't your first peak be, you know, somewhere close to 0, corresponding to the first electron removed? The next electron removed would be a little bit farther. So their question is, shouldn't your spectrum or spectrogram look more like this? So there's the first electron, there's the second one, there's the third one, there's the fourth and fifth and sixth and seventh and eighth, and that empties out the valence shell of neon. And then you'll have a ninth electron and a 10th electron that have significantly more ionization energy than all the ones in the valence shell. Well, you're onto something, but this isn't how photoelectron spectroscopy works. See, photoelectron spectroscopy is not successively removing electrons from the same atom. Instead, you're firing these beams at millions and billions of atoms. Some atoms, you will strike them with beams that eject one of their 1s electrons but leaves all of their other electrons untouched. Some of the beams will hit other atoms and eject their 2p electrons, for example. And so when you're ejecting electrons from, the 2p orbitals of millions and millions of atoms, and some of them are ejecting the 2s electrons from millions and millions of atoms, and some of them are ejecting the 1s electrons from millions and millions of atoms, you're kind of playing with probability, but since you have so many atoms, it's practically guaranteed that the number of 2p electrons that come out of some of your neon atoms will be about 3 times as many electrons that come out of your 2s subshells. And also, I guess, 3 times as many as coming out of your 1s subshells. So maybe I should take a sip of water. That's how you know you've been talking for too long. I think my throat is telling me that this video has gone on for long enough. Where was I? Lost my train of thought again. What was I saying? Okay, so suppose you fire a bunch of X-ray beams at... let's just keep it simple and say we fired it at 1,000 neon atoms. 1,000 neon atoms. Okay. Maybe for, let's see, 600 of them. 600 of the neon atoms we hit them in such a way that we got out a 2p electron. Just one of the 6 2p electrons. So 600 neon atoms, roughly, they gave us their 2p electron. The 2p electron was ejected out of 600 of them. 200 of them ejected the 2s electrons that they had. And 200 of them ejected the 1s electrons that they had. Now, those numbers are probably not what you're going to get in real life. Maybe if you did the experiment in real life, 580 of them would give you the electrons out of the 2p, and 215 of them would give you the ones from the 2s, and 205 of them would eject electrons from the 1s level. But still, on your spectrogram, the ratios will still look like 1 to 1 to 3, and the p electrons that you're ejecting, they're not going to be successive p electrons because it's very, very unlikely that you're going to hit the same atom twice. So essentially, when you eject the 2p electron out of 600 neon atoms, you're just ejecting the first out of 6 of them from that particular atom. I may not be wording this very well. Maybe it's because I'm too exhausted at this point. Should I just drop it and leave the explanation in a comment? I don't think a wordy explanation in a comment would be as helpful. Let me try and put together the words here. Just give me a minute. Okay, let me draw a couple of neon atoms. So here's one neon atom. And yeah, this blue marker is as good as dead. Let's see, what should I use to replace it? I guess I can go with a dark green. Okay, so there's 2 electrons there. And there's 8 electrons there. Let's draw another one. Maybe I shouldn't have been so quick to throw out the blue. Let me draw it here. So there's neon. Okay, I am using a Bohr model here, but let's pretend that 6 out of these 8 electrons are in the 2p orbital and are a little bit further out from the nucleus than the other 2. So let's say that these are in the 2s and are actually a little bit closer to the nucleus than the other 6, and same thing here. Let's say those are from the 2s. So if I fire a bunch of X-ray beams on a bunch of neon atoms, let's say I hit one neon atom such that I eject 1 electron out of the 2p level. If I eject more electrons out of the 2p level, they'll still be the first 2p electron. They'll still be the first ionization energy because it's for a different atom. Uh-oh, did I lose my camera? It looks like I did. Let me try and reconfigure it real quick. Let's see, is it working? Oh, great. Perfect timing. Let's see. Properties. Okay, let's try that. Let me try and refocus it. Okay, I think we are back in business. Okay, I don't know how much of that you missed because I didn't notice the thing going off, but where was I? Right, so let's see, considering these as 2s electrons and considering the rest of the electrons in the second shell to be 2p electrons, if I fire a beam of X-rays at a bunch of neon atoms and one of them hits a neon atom such that it ejects a 2p electron, so basically the energy of that X-ray beam would correspond to the first ionization energy of that neon atom. Then the next 2p electron I eject is also going to correspond to the first ionization energy of the neon atom because it's going to be taken from a different neon atom. It's very, very unlikely that you take 2 electrons from the same atom, and even if you do, it's not going to be significant enough to matter. It's not going to be significant enough to mess up your graph so badly that you can't tell that there's a very clear ratio of numbers of electrons being detected at different energies. So, in fact, a real graph might be a little smudged. So, take this graph, which is more ideal, and let's say you do coincidentally hit a couple of your neon atoms twice. Let's say you do, and let's say a couple times I might actually take 1 electron from the 2p and then take a second electron from the 2p of neon. If that happens some of the time, then you might see a little bit of smudging around here. You might see a little bit of that. But overall, it's not going to be significant. You're not going to see a significant amount of that happening, so you can rest assured that all of the 2p electrons, or virtually all of them, are going to require the same energy because they're being taken from different atoms. So you don't have to worry about successive ionization energies. Okay, was there anything else? Another common question regarding photoelectron spectroscopy. I know there was one more. Give me a minute to think about it. There was another question, and I saw this one online recently too. Oh, right, for physics students. So, if you know your physics, then you might have heard of something called the work function. You might have heard of something called the work function. So this is physics stuff. If you don't want to pay attention to it, you don't have to. So if you studied the photoelectric effect, then you might remember something called the work function, which is the minimum energy needed to start ejecting electrons from a metal. And this notion of ionization energy or binding energy, the energy needed to eject an electron from an atom, is a very similar concept. In fact, you might think it's the same, but there is one notable difference. They are kind of the same, except for one thing. The work function is about the easiest electrons you can get. The work function is the minimum energy you need to put in to start ejecting electrons from the, typically it's a metal, but I guess it could be a non-metal. From the substance, let's just be general about it. The work function is the lowest energy possible where you can start ejecting electrons. In other words, the work function corresponds to the lowest energy peak, you could say. The work function is the energy required to get the most gettable electrons, the ones that are farthest out from the nucleus, the valence electrons, while binding energy / ionization energy is going to be broader. It's going to include electrons on all sorts of different levels, whereas the photoelectric effect is more about valence electrons than anything else. So there's that question answered. I think that takes care of everything I had to say about photoelectron spectroscopy. If I remember anything else, I'll just mention it in a pinned comment. Oh yes, there is a practice quiz. Should have mentioned that before dismissing the chemistry students. Oh well, they'll find it. There is a practice quiz that I found online, which is really good because it grades you as you go through it. It doesn't just grade you at the end. And I really like that. So I'll be posting a link. To a PES quiz. Posting a link to a PES quiz, and I'll put that in my usual pinned comment. So take the quiz, practice, practice, practice. And yeah, I think that's everything I have to say now, for real this time. Next week, or not next week, I don't even know if it's going to be next week or maybe it'll be in a couple days, but next video we're going to be doing probably my favorite part of the course, where we get to play with the 3D models a little bit. We're going to look at shapes of molecules and polyatomic ions, and we're going to dig deeper into Lewis structures and how to interpret them, how to look at the 2D Lewis structure and picture what the molecule or ion looks like in 3D. So that's what's coming up next. I hope you're looking forward to it as much as I am. But lost my train of thought again. What was I gonna say? Oh well, I'll remember it later and probably post it in a comment, or I'll remember that it was insignificant. Anyway, this has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I'll see you in the next video.